All of you, can you hear me? Just power came. So just 1 minute. Let me switch off the fan and I'll switch on the AC. Just 1 minute. Just power came. But I'm trying to do alternative. Right. So all of you, can you see? Raise the hands. Right. So just power came. So I was like waiting. But since morning, the same issue I had here. Why? Because since a week there was heavy rains, and due to that, these trees and other things, so they collapsed. So we have the issue with that. So anyhow, I'll continue. Right. Fine. See, if one question doubt, if leakage reactance is less, leakage flux should be high, no sir. See, already I have explained this. Please refer to my notes. What is the relation we have between the leakage flux and leakage reactance? That was already explained, my dear Ravindra Kumar Singh. That was already explained. Please go through that. Fine. So let me continue with the class. So what is the relation we had between the torque at uh, starting and the torque with maximum load? Means we have seen one relation. So maybe relation number 6, if I'm correct. So what is the relation number 6? T start by T max is equal to 2 SMT by SMT square plus 1. So this equation we can use to find out the torque, to find out the additional resistance for any torque at starting. See, one thing, roughly some 60 to 70% of syllabus we have finished. So the coming session will be after today's session. That is the very important concepts in induction motor, the starting methods, the speed control techniques. All those are very important concepts, right? Please try to be more attentive in those classes. And tomorrow anyhow we'll be having holiday. Why? Because you know what is the reason for that. So tomorrow there will not be any class. Again, our class will be from Monday onwards, right? So this is the relation what we have seen in the last class, right? Equation number 7 is, I want to find out the ratio of full load torque to maximum torque. What is that ratio? So again, I'll go for that equation 5. What is that equation 5 says that the ratio of torque at any slip by maximum torque is equal to something we have derived. Now I want to find out the ratio of full load torque to maximum torque. So if I want to find out the ratio of full load torque to maximum torque, so in place of that, yes, I write TFL by T max, that is equal to 2 SMT SFL by SMT square plus SFL square. So in place of S, I wrote SFL. Why? Because when S is equal to SFL, the electromagnetic torque is nothing but the full load torque value. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. So before we proceed to the next content, next equation, I'll be asking one question. I think this is the thing which you generally see every day. If you switch on the fan Then if you observe that fan, then you can see the fan initially rotate, it will accelerate up to certain speed. After certain speed, then the motor will not further accelerate, it will come to a steady state operation. Why there is an initial acceleration after reaching a particular speed? Why there is no acceleration? What is the reason that the motor will be rotating with that particular speed? So can you please tell me? So if you look into that fan, if you give the excitation, if you switch on, then you can see that fan will be initially accelerating, the speed will be initially increasing. After reaching certain speed, after reaching certain value of the speed, there will not be any further acceleration. The motor will continues to rotate with that particular speed, with that fixed speed, right? So can you please tell me what may be the reason for that? Can you please text me? Text me. Inertia. Initially inductive, after resistive increases. To overcome inertia, up to rated current it rotates and full load rotates. TFL, NS, starting torque is less. Due to inertia of the rotor, due to inertia, rated speed of the motor is achieved. External resistance will cut off. See, you are cutting off any external resistor there in the fan? No. So load torque equal to electromagnetic torque, anonymous attendee, good. Due to friction, wind friction is equal to torque speed. T load is equal to TEM. Excellent. Anyhow, I'll answer to that question. Just don't text now. It is enough. I'll answer to that question. Why that motor will initially accelerate after reaching a particular speed? Why it will not further accelerate? Why the motor will try to rotate with that particular speed? Right? We will see all those things step by step. Right? Before to that, let me finish this equation. So what is the relation we are having between full load torque to maximum torque means? It is like this. So using this equation, I can find out some numerical. What is that? I'm having a induction motor. The maximum torque of that motor is 99.87 Newton meter, and it occurs when the slip of motor is 0.141. If the full load slip of the motor is say 0.04, so can you please tell me what is the full load torque value? Yes, I can use this formula. The full load torque value by maximum torque is how much? 99.87, 2 into 0.141 into 0.04 by 0.141 square plus 0.04 square. If you solve this, then you can get the full load torque of that motor to be 52.38 Newton meter. Like that, I can use this equation number 7, right? So if you know the maximum torque value, and if you know the slip at that maximum torque, and if you know the full load slip of the motor, and if you want to calculate full load torque value, you can use this formula. Is this point clear? Confirm me all of you. Confirm me all of you. Right, done, enough. Now what I want to do means, I want to find out what is this 7, 8. I want to find out the ratio of starting torque to full load torque. So for this, what I'll try to do means, I'll divide numerator and denominator with T max. T max. Why? Because I have the relation T start by T max. What is the relation we are having? T start by T max. It is 2 into SMT by SMT square plus 1 by 2 into SMT into SFL by SMT square plus SFL square. So here you can see 2 SMT will get cancelled. Then if I simplify this, I'll get SMT square plus SFL square by SFL into SMT square plus 1. So SMT is the slip at maximum torque. Is this point clear? Confirm me, all of you. Confirm me, all of you. Right. Only few. What happens to others? Please raise, all of you. Right. Then equation number 9. What is that equation number 9? Already I told you that. What is that? We have a wide range of slip for an induction motor. What is the wide range of slip? It is 0 to 1 per unit or 0 to 100%. Even though we are having a very wide range of slip, the operating slip is only 2 to 8%. It should be less than 10%. Why we are not supposed to operate the motor for higher value of slip means the machine performance will be very, very poor. Why? Because the rotor speed will be away from synchronous speed, then flux cuttings will be more, EMFs in the rotor conductors will be more, currents will be more, ohmic losses will be more, efficiency will be less, the motor will get heated up, everything will be like destructive. So that is the reason we are not supposed to operate the motor with larger value of slip. Always we are supposed to operate the motor with smaller value of slip. Already I told this point. Is it clear? Confirm me. Is it clear? Confirm me. Now, so if you want to know the equation for torque for low slips, you can use for low slips, NR is closer to NS and slip is approximately equal to 0. If that is the case, R2 by S whole square will be much greater than X2 naught square. Then I can say R2 square is much greater than yes, X2 naught square. Then for low value of slip, if you take this torque equation, electromagnetic torque 180 by 2 pi ns S E2 naught square into R2 by R2 square plus S X2 naught whole square. So in this, you can see this S X2 naught whole square can be neglected. So electromagnetic torque is equal to, I can see 180 by 2 pi ns S E2 naught square into R2 by R2 square. 1 R2 will get cancelled. Then finally, what is the equation we are having for electromagnetic torque? So electromagnetic torque is equal to 180 by 2 pi ns S E2 naught square by R2. So this is the equation which you can use for low values of slip. So what is the equation we are having for general slip? So this one is the general slip. But you know that the low operating slip is the operating region for your induction motor, right? So tomorrow they may ask the question like this: a three-phase induction motor, E2 naught is given, R2 is given, but X2 naught is not given. You are asked to calculate the full load torque. Then in that case, you can use this formula. How? So electromagnetic torque is equal to 180 by 2 pi ns SFL E2 naught square by R2 if the operating slip is very less. I hope this point is clear. All of you confirm me. Confirm me. So let me check. So it is very less. Let me check. What does that mean? Yesterday we have calculated the full load torque of the motor. What is the full load torque of the motor we got? It is 52.38 Newton meter when you have considered both R2 and X2 naught. So here I'll be neglecting yes X2 naught and be calculating the full load torque. Please help me with the answers now. So full load torque is equal to 180 by, just answer me, 1000.04 into 76.98 whole square by 0.12. So can you please tell me what is the answer for this? Can you please tell me what is the answer for this? Text me. 56.58. See, today's class is not your last class, Baba. How can you say today class is the last class? So many things are there pending. I never said today class is last class. See, I don't know this anonymous attendee. He is very much curious to know how long or how much time. See, Baba, please try to be patient. So as I told you that I'm not running away with the time and I'm not like killing your time. See, my intention is I have to complete your syllabus, right, with the subject. So please try to understand that. Today is not the last class. Again, next week we'll be having. Tomorrow is a holiday for you, I told. So 55.3, some got 55, some got 56. 56 point, I don't know, some told 53, 55.3, 56.58. So I go with 56.58, 58, right? You can see these values, if I round this to 56, if I round this to 52, so you can see more or less 4 Newton meter difference, 4 Newton meter difference. So you can use this formula when your operating slip is very, very less. Why? Because during low slip operations, that Sx2 naught whole square will be much lesser compared to your R2 square. That is the reason we can ignore this. Is this point clear? Confirm me. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. So please, I'm trying to tell you all the possible ways. Next one is equation 10. Very, very important equation. Equation 10. If I take the stator to rotor turns ratio to be 1, then E1 is equal to V is equal to E2 naught. Why? Because you are taking the turns ratio to be 1. So in this case, what will be the electromagnetic torque? It is 180 by 2 pi ns S V square by R2. Right? 180 by 2 pi ns S V square by R2. Then if I still modify this, I just do this. So in this there is one F. So finally I can say this electromagnetic torque is directly proportional to S V square by F. Why? Because once the motor design is completed, so we cannot change the values of R2, X2 naught, poles and other things. So what are the things we can change means externally the magnitude of the supply voltage and the frequency and the slip. So tomorrow the question may be asked, see, please, see, a three-phase induction motor is designed for a 50 hertz supply, designed for a 50 hertz supply and 400 volts, designed for a 50 hertz supply, 400 volts, and it is operating with a slip of 4%, operating with a slip of 4%. But fortunately or unfortunately, this induction motor is excited with 400 volts and 60 hertz supply. 60 hertz supply. Then for the same slip, what will be the torque developed by this motor? Will it increase or will it decrease? I'll repeat once again. Initially, I'm having a induction motor, and initially that induction motor is excited with 400 volts and 50 hertz supply, and it is operating with a slip of 4% and developing some torque T. Torque T. Up to here clear, confirm. Up to here clear, confirming. Right. But unfortunately, if the same motor is fed with a 400 volts, 60 hertz supply, then at the same slip of 4%, what happened to the torque value? Will it be more than that or will it be less than that? So my answer, your answer should be it is more than that or less than that. You can see voltage is fixed, slip is fixed, then torque is inversely proportional to frequency. Now the frequency of the supply is increased from 50 to 60. When the frequency is increased from 50 to 60, what happened to the torque compared to that 50 hertz? So when compared to the 50 hertz, the torque will be less. Then your answer should be less. So it is less. Like that, they may ask, they may frame some questions basing on this. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. See, Baba, I'm just highlighting all the possible ways the questions can be asked. I'm not leaving any content or concept as of now. So these are some equations. Before I proceed further, so let me see what are the things we can calculate now. Just I'm revising. See what is the data that is given in any numerical. R2 is given, X2 naught are given, poles are given, right? The supply frequency is given and E2 naught is given. So how many ways that E2 naught can be given? 3 ways. Already you have seen are given. Are given. If you want to calculate the machine performance when operating at slip yes. First, what is that you need to find out? First one is you need to calculate I2. E2 naught upon square root of R2 by S whole square plus X2 naught whole square. You can find out. Is it clear? Confirm me. After that, you can calculate the rotor input power. After that, you can calculate the rotor losses. After that, you can calculate the rotor output power. And also you can calculate the electromagnetic torque. So these are the things which you can find out if the rotor circuit parameters are given. In addition to that, in addition to this, what are the things we can find out? The full load torque, the starting torque, the maximum torque, the external resistance for maximum torque at starting, the maximum internal mechanical power. So these are the things which you can find out. Is it clear? Confirm me. Is it clear? Confirm me. Right. So this is what we have discussed. So if anyone questions you, Are Baba, what is that you have learned as of now? As of now. Then you can say, our teacher has explained about the basic laws, the constructional details, the concept of RMF, the working principle of a three-phase induction motor, how to represent the rotor circuit electrically, and using that rotor equivalent circuit, how to find out the performance of the motor. This is what your teacher has explained as of now. Is it clear? Confirm me. Is it clear? Right. The next one is the types of mechanical loads. The types of mechanical loads. Types of mechanical loads. Mechanical loads. Mechanical loads. So tomorrow, if any question is given, you should say, oh, I know everything. What is the need to worry? So you please tell me what is the data you have given, what is it you want. See, any question will be basing on the performance. Then the data will be given accordingly, you can answer. Types of mechanical loads, right? So, see, sir, could you please tell me why you neglected X2 naught? Baba, I didn't neglected X2 naught. I neglected yes X2 naught wholes. So when compared to R2 square, during low slip operations, yes, X2 naught whole square is very, very less. That is the reason I have neglected. I have not neglected X2 naught. You can see. So already I wrote here, I didn't neglect X2 naught. You can see here, during low slip operation, this is the condition. For that, I have neglected. I hope this point is clear. Confirm all of you. Confirm all of you. Right. So one more. So one student, anonymous attendee, sir, how to find out the power factor? So he didn't mention whether the rotor power factor or the stator power factor. If it is the rotor power factor, already I gave the formulas. Please try to refer the formulas. Rotor power factor is equal to R2 by Z2 and try to get that. Please, you'll get the answer for that. Please. Fine. Now I have to raise one question. Let me see how many of you will give the answer for this. See, whenever I am talking about generator, so the output of a generator is electrical, and I can use that electrical power for many applications. So generator means it will give electrical output power. Similarly, when I'm talking about motor, So motor output power is mechanical, nothing but a rotational energy. Now my question to you people is, when we are having DC motors, when we are having induction motors, when we are having synchronous motors, when we are having the special motors like stepper, reluctance and other motors, what is the specific reason that in most of the domestic applications, the agriculture applications, the industrial applications, the official applications, we are using induction motors, right? So don't try to give the answer that the available supply is AC, the construction is simple. Like that, don't try to give the answers. Please try to give the technical point, technical aspects, why we are using induction motor when the other motors can also give a mechanical energy, just like your induction motor, to rotate, when the other motors can also be used to rotate something, fan or something else. What is the specific reason that we are using only induction motors in most of the application? It is something like a black horse in the industries. What is the main reason for that? Please try to give the answers for that. I told you that don't say that simple construction, low speed regulation, available supply is AC, speed control is easy. Like that, you don't tell the advantages. You please try to tell some technical points, technical aspects, why we are using induction motors. Self-starting. See, even single phase is not self-starting, but we start and use, right? Requires only one source, sir. We can get starting torque as per our requirement. Self-starting, no problem of synchronization. Separate excitation for rotor not required. Single excitation is enough because it is a single excited machine. So robust and easy maintenance, right? Induction motor, we give supply only to stator, less losses. You can use for wide range of, right, constant speed. Only one supply to the stator, robust and easy maintenance, no need of given field supply. AC supply is ready. I told not, don't give all those things. Induction motor is a constant speed, low, robust and less maintenance. Efficiency is more. Single excited, double layer winding. It is a variable speed device, reliable and economical. Torque consideration and economical efficiency. So no one is giving the what is the true answer. Induction motor is a synchronous motor, variable. Okay, leave it. Enough. Don't text. Enough. So enough. But I have seen nearly some 50 to 60 answers, but no one has given the exact and true answer. Anyhow, I'll explain that. Right. So what is the true reason that we are using mostly induction motors? Right. Someone is curious to give again. Right. Right. Anyhow, no right answer. No right answer. Right. Anyhow, I'll explain that. So if I have to explain that why we are using induction motor in most of the applications, then first of all, you should know the types of mechanical loads. If you know the types of mechanical loads, then you can understand why we are using induction motor in most of our applications, right? To drive or to produce mechanical power. So let me explain the types of mechanical loads. Mechanical loads. Sir, we know something about electrical loads like R, L, and C loads, but we didn't come across what are called as mechanical loads. What do you mean by mechanical loads? Yes. So in simple terminology, in very cut short manner, so if I want to operate the electrical appliances like lamp and other things, we need an electrical energy. Similarly, if I want to rotate something, I need a mechanical energy. So if I want to rotate a fan, I need a mechanical energy. If I want to rotate a mixer, I need a mechanical energy. If I want to rotate or if I want to move a lift, I need a mechanical energy. If I want to move a traction, I need a mechanical energy, right? So for all electrical applicants, right, we need electrical. For all mechanical which need rotational, we need mechanical energy. Is it clear? Confirm me. Confirm me. Right. So my first mechanical load, I'll tell. My first mechanical load is, if I look into the fan, just if I raise my head and if I look into the fan, so we need mechanical energy to rotate the blades. It looks like we rotate the blades. So in order to rotate the blades, we need mechanical energy, right? So what is the load on the motor? So load on the motor means it is something like this. See, I'll give an example. See, I'm having a motor here, right, a shaft here, and I'm having a trolley, power cut, I think, right? Trolley, no problem, but no problem. Backup is there, 100% safe. Trolley, in that cage, in that, say there is some 100 kg weight, 100 kg weight. Then if I ask what is the load on the motor, means I'll say 100 kg weight. So whatever the torque the motor has to develop, it has to pull or move this 100 kgs weight. So what is the load on the motor means 100 kg weight, and it is a constant weight or constant load. Why? Because at starting, whatever the load we have on the shaft, the same load is there while the motor is operating or when the trolley is being moved. So the load on the motor is constant. Will agree with me? All of you tell. Will agree with me? Right. Similarly, if you look into the fan, what is that we are using inside? Motor. So what is that motor has to drive? What is the load on the motor? What is the load on the motor? Or what is that it has to rotate? What is that it has to drive? Means the people can say by looking into that, the blades or the wings, right? So the load on the motor is the wings or the blades, right? But truly speaking, the load on the motor is not the wings, the load on the motor is not the blades, but the load on the motor is the wind friction. The load on the motor is the wind friction. So this fan comes under which type of mechanical load? Means this fan comes under which type of mechanical load? Means the load torques whose magnitude varies with the square of the speed. The load torque whose magnitude varies with the square of the speed. What do you mean by that? At starting, the load on the motor is zero. Why the load on the motor is zero? Why? Because the blades are stationary. The air is still stationary. So there is no opposition to the rotor rotation, neglecting that windage and frictional losses inside. There is no opposition. But once you can see, if the fan or if the blade starts rotating, when the blade starts rotating, the air around will also be in motion. When the air around is in motion, that air is converted into wind, and that wind will be opposing the rotor rotation. So any opposition to the electromagnetic torque, any opposition to the rotor rotation, we call it as a load on the motor. So once the fan starts rotating, once the blade starts rotating, then you can see the air will be in motion, and that air which is in motion is nothing but a wind, and that wind will be opposing the rotor rotation, and as it is acting as a load on the motor. So what is the true load in case of fan? Means it is not the blades, it is the wind friction. It is the wind friction. So it comes under variable load or it comes under a fixed load. Means it comes under a variable load. Why? Because at starting, the wind opposition is almost zero, the load on the motor is zero. But once the motor starts rotating, as the blade starts rotating, the wind also will start moving, and it is opposing the rotation, and it is acting as a load on the blades or load on the shaft. So it is acting as a load. So it comes under which type of mechanical load? Means the load torque whose magnitude varies with square of the speed. So this is the fan load. This is the fan load. So can you please tell me, it is a variable load or a fixed load? It is a variable load. Variable load. Variable load. So it is a falling load or a rising load? It is a rising load. A rising load. So the true load is the blades or the wind friction? The wind friction. Wind friction. Wind friction. Is it clear? Confirm me all these 3 points clear. So these are all the experimental results. Is it clear? I need all to raise the hands. Right. Fine. So once again, I'm repeating. So if you look into this fan, so what is that energy that is required to rotate that blades? Means it is the mechanical energy. So what is the load on that mechanical energy? Means it looks like the blades, but truly speaking, the load on the motor is not the blades. The load on the motor is the wind opposition, the wind friction. So what is the load value at starting? The load value at starting is almost zero, but once the fan starts rotating, the load on the motor is increasing. The load on the motor is increasing. So at starting, TL is zero, right? That means what is the load on the motor at starting? The load on the motor at starting is zero. That means if I want to rotate this load, I need a motor with low starting torque or high starting torque. Low starting torque is enough, right? But you can see once the motor starts running, what happened to this load torque value is increasing. Similarly, once the motor starts rotating, then the motor torque should be increasing. So which motor have the similar characteristics as the load? So here, what is the characteristics of the load? It is a rising load characteristics. At starting, the load value on the motor is zero, but once the motor starts rotating, the load value on the motor shaft is increasing. So if I want to rotate this fan, if I want to rotate this mechanical load, then I need a motor whose characteristics are very similar to the load characteristic. That means at starting, the motor torque should be less, and once the motor starts rotating, the motor torque has to be increasing. So which motor have the similar characteristics? Means a squirrel cage induction motor. Why? Because at starting, as the rotor frequencies are equal to the supply frequencies, the rotor circuit is high inductive in nature, the starting torque is less. So this small torque is enough to drive the fans, drive the blades. But once the motor starts rotating, this load torque is increasing. At the same time, the motor torque will also increases. Why? Because once the motor starts rotating, the frequencies of the rotor current starts decreasing, then the inductive nature of the rotor circuit starts decreasing, and hence the motor torque will increase. So can I say in fan applications, so what is the type of that mechanical load? Means it is the raising load characteristics. So it is something like square of the rotor speed. So if I want to drive that load, then the motor should have the similar characteristics. Even the motor torque should be rising. So which motor have the similar characteristics? Means squirrel gauge. At starting, the torque is less. This torque is enough to drive the load, but once the motor starts rotating, the load torque increases, even the motor torque is also increasing. So here you can see the characteristics of a cage rotor and the characteristics of that mechanical load, both are same. So that is the reason we are using which motor in that particular fan application. Means squirrel gauge motor. Is this point clear? Confirm me. See, I told you that it is the experimental result. So please, one thing, if something is required, I know how to derive. So it is, if you go for experimental result, so it is basing on that, right? Please, when I write something, it is basing on the experimental result. So experimental result doesn't need any mathematical proof. Please, Baba. So which motor I can use? Means there is no need to go for slip ring. I can go for squirrel gauge induction motor. I hope this point is very, very clear. Please confirm me. Right. Once again, I repeat. So this fan comes under which type of mechanical load? Means this fan comes under the load whose torque varies with square of the speed. Whose torque varies with square of the speed. At starting, what is the load on the motor? At starting, the load on the motor is zero. Once the motor starts rotating, the load on the motor will increase. So no one is manually increasing, but once the blade starts rotating, the wind opposition will also increases, the load on the motor will be increasing. So in order to drive that, I need a motor with the similar characteristics. So which motor have the similar characteristics? Means squirrel gauge induction motor. So in this particular fan application, which motor is best suited? Means squirrel gauge. Why? Because the load characteristics are rising, even cage rotor characteristics are also rising characteristics. That is the reason I can use a squirrel gauge induction motor in this particular fan application. Is this point clear? Confirm me. Right. So one fellow, right, wrote, sir, why not slip ring induction motor? I tell you one thing. Say I'm having a small stone. So if you want to move that small stone, a kid is enough to move a small stone. But a Bahubali is not required to move that stone. Okay. If I'm talking about a slip ring induction motor, the main purpose of a slip ring induction motor is to drive heavy loads, right? So if I'm having a 100 kg weight, then I need a Bahubali to move that. So the slip ring induction motors are not used when the starting torque requirements are very less, right? Is it clear, Baba? Right? Is it clear? Ashish Raj, right? Done. Fine, no problem. So if I'm trying to plot these characteristics, you can see here. So it is a raising load characteristics. Raising load characteristics. Then what is the relation we are having between torque and power? You know that P net is equal to torque into omega R. So this torque is directly proportional to square of the speed into one more speed. So this mechanical power will be directly proportional to cube of the speed. So in recently one of the competitive examination, this question was asked. What is that? Please see. A three-phase induction motor is driving a fan load and operating at a step of N with a torque T with a power P. A three-phase induction motor is driving a fan load operating with a speed N, right, with a developed torque T and with output mechanical power of P. Is it clear up to here? Is it clear? Right. The question is, the speed of the motor is reduced to N by 2. The speed of the motor is reduced to N by 2. Then what happened to the values of torque and what happened to the values of mechanical power? Simple. When the speed is reduced to half, then the torque will be reduced to 1 by 4 and power will be reduced to 1 by 8. Why? Because torque is directly proportional to N square, power is directly proportional to N cube. When speed is reduced, then the required torque will be reduced to T by 4 and the mechanical power will be reduced to T by 8. I think this point is clear. Confirm me all of you. Confirm me all of you. Right. So this is something about your first type of mechanical load. I will repeat once again. So we have many, but according to our syllabus, I'm considering only few, right? So this fan comes under which type of mechanic? See how N cube. See, it is very much clear here. This torque is directly proportional to N square. In this, there is one N. So N square into N square, N is how much it is? N cube. Please try to calculate, Baba, anonymous attendee. Please try to see. Is it clear now? How N cube? Right. Fine. So this is something about your first load, right? The second one is the mixer load. The mixer load. Mixer load means don't imagine your household mixers. I'm talking about the giant mixers. So they comes under the load whose magnitude varies with speed. Again, you can see this is also raising load, right? So when the load torque is varying with the speed, then the mechanical power developed will vary with square of the speed, right? So this is also a rising torque load, a raising torque load. So in this case, which motor again we can use? Again, I can use a squirrel cage induction motor only. Why? Because here, in case of this raising torque, starting the load torque value is less, and with the increase in speed, the load torque value is increasing. Then I can go for a induction motor here, right? Which motor I can use? A squirrel cage induction motor I can use. Is this point clear? Confirm me. Right. See, when I said we are using a cage motor means, again, one of the student has mentioned, sir, which motor for ceiling fan in our houses? Squirrel cage induction motor only. Repeatedly, I'm telling, if you raise the hand, raise the head, then you can see one fan, and in that the motor which we are using is a cage rotor. Why? Because the characteristics of the load and the characteristics of the motor both are matching. That is the reason we are using a cage rotor. But the fact is we use a single phase there, right? Is it clear? Confirm me all of you. Confirm me all of you. Right. The second one is the mixer load, the load torque which varies with speed. Again, it is a rising load or it is a falling load. Again, it is a rising load. What is the load value at starting? It is almost to zero. Then to drive that, I need a motor with a low starting torque. So which motor is having low starting torque means a cage motor. But with the increase in speed, the load on the motor is increasing. So here the motor which we are using should have a increasing motor torque. So which motor is having the similar characteristics means cage motor. So in this case also we use a cage motor, right? Cage motor will use. I think this point is clear, right? So please try to tell me again, it is a rising load characteristics or falling load characteristics. It is a rising load characteristics. So for all rising load characteristics, we use a cage motor. We use a cage motor. We use a cage motor, squirrel cage induction motor. I hope this point is clear. Confirm me all of you. See, I don't know whether to answer this question or not to answer to this question. Sir, why do we use single phase induction motor in ceiling fan? See, what is the supply available at your house or in your house? It is a single phase. It is a single phase induction motor, and that is enough to drive that required wind friction. That is the reason we are using only single phase. Right? Please, Baba, try to right. Fine. So in the second case, what is the power? Power is directly proportional to NR square. So again, which motor I can use here? It is the squirrel cage induction motors. Now next one is in first case and in the second case. So we are varying the load on the motor manually or the load is varied automatically. So the load on the motor is varied automatically. We are not varying the load manually. Second case is the load on the motor is a physical load or it is a wind friction or wind opposition. The load on the motor is a wind opposition or wind friction. So it is not a physical load, it is a wind opposition. So 2 points to be noted here. One point is in case 1 and case 2, we are not varying the load on the motor manually. The load on the motor is varied automatically. How? As the speed of the rotation increases, the wind opposition will increase and hence the load on the motor will vary automatically, right? Second point, it is the true mechanical, it is the wind friction. It is the wind friction. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. Third case is case 3 is low torque is constant. Low torque is constant. What is the meaning of low torque is constant? It is the constant torque load. So whatever the load we have at starting, even during running also, the load on the motor is same. The load on the motor is same. So what is the best example for your so-called as constant torque load means your lift. So here also which motor I can use means I can use a squirrel cage induction motor only basing on the number of capacities. That means if I'm having a smaller lift, say which can carry 2 persons, then I can use a small HP motor which has a capacity to drive that maximum 2%. If the number of persons in that lift is increased, then the rating of that motor has to be increased. I can go for a bigger HP motor. But we don't have any lift which can carry 100 people, right? Up to some 10, 12. So accordingly, we can use a squirrel gauge motor. So there we can use a squirrel gauge motor. So there also which motor we can use in lift applications. It is nothing but your squirrel gauge induction motor. Is this point clear? Confirm me. Is it clear? See, I told you mixer load means the giant mixers which you are using for mixing up cements. So you can see the giant mixers I told, right? Please, right? Fine. So the best example for this is the lift applications. So it is a constant torque load. Then what is the relation we are having? P net is directly proportional to speed, right? Why? Because P net is equal to torque into omega R. So here torque is constant. So P net is directly proportional to NR. So the power will be increasing linearly. So what is the motor I can use here? I can use a squirrel gauge induction motor. So First case is the load torque whose magnitude varies with square of the speed. So it is a raising load characteristics. Then in that particular case, we need a motor with raising torque. So which motor is having a raising torque means cage rotor. So in that particular fan applications, we go with a squirrel cage induction motor. Of course, it is a single phase there. Second one is the mixers, right? The giant mixers. So they comes under the load torque, right? Whose magnitude varies with the speed, right? At starting, what is the load on the motor? It is almost to zero. With the increase in speed, the load on the motor will be increasing. Again, which motor I have to use in that particular case means I need a motor with the raising load, raising motor characteristics. Again, which motor is having the raising characteristics means cage motor. Even in that case also we use a cage motor. Third one is a constant torque. What is the meaning of constant torque? So whatever the load we have on motor at starting, even during running also, the load on the motor will remain same. So in that application also, basing on the magnitude of the load, I use the range of the motor. If the load on the motor is a 10 kgs, I use a 1 HP motor. Just I'm giving example. With the increase in load, I can increase the rating of the motor. So in this case also, we can use which motor? A cage motor. Is this point clear? Confirm me, all of you. Is this point clear? Confirm me. Right. The last one is the traction load, case 4. I'm talking only few loads. Traction loads. Traction means your electric traction. Crane loads. So they comes under the load torque whose magnitude is inversely proportional to speed. What is the meaning of whose load torque magnitude is inversely proportional to speed? Means when the speed of the motor is zero, the load on the motor is maximum. And when you are increasing the speed, the load on the motor will be decreasing. So these are called as falling characteristics. Falling characteristics. So this comes under falling characteristics, right? But if I take a squirrel cage induction motor, the squirrel cage induction motor is having a raising characteristic. So for example, if I'm using this cage motor in traction in your engine, electrical engine, what is the load on that electrical engine? The 24 coaches and the person sitting in that coaches is the load on the motor. So is it possible for that cage motor to drive that load? No. Why? Because the starting torque of that motor is very, very poor. So which motor I can use in that particular application means I can use a slip ring induction motor with high resistance in the rotor circuit, or I can use a series motor. So in this particular application, I can use a slip ring induction motor with an added resistance, or I can use a series motor. Why? Because the starting torque of that series motor is very, 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 very high, right? So can I say like this? Can I say like this? So it is true that all the motors will give the mechanical energy. They have the capacity to rotate the mechanical loads. But it doesn't mean that we can use motors for whatever the applications we have. No. First, what is that we need to check? First, we need to check the characteristics of the load. So you are able to hear me? All of you are able to hear me? See, Baba? Right. So maybe few people are having some technical issues. Please try to rectify. Right. See, whenever you are selecting a particular motor for a particular application, first you need to check that the characteristics of the load. The characteristics of the load and the characteristics of the motor has to be matched. Then only in that particular application we can use the particular motor. For example, say in this fan application, I'm using a series motor. When I'm using a series motor, then the load will talk to the motor inside. My load value on you at starting is very less, then the motor will respond to the load. My torque value is very high. Then in that case, what happened? This fan will rotate with dangerously high speeds. And if that bearings or if that mechanical settings, if they are not able to withstand such high speeds, then definitely that fan is going to be damaged. So that's the reason in this particular fan application, we don't use either a slip ring induction motor with extra resistance, or we cannot use a series motor. So in this particular application, which motor we have to use? We have to use a cage motor. If I take a traction, So in the traction, if I'm using a cage motor, so the cage motor can drive that load. Why? Because the starting torque is less. So in that particular application, we have to use either a slip ring induction motor with resistance, or we can use a series motor. Like that, basing on the load characteristics, we need to select a motor for that particular application. It doesn't mean that every motor will give a mechanical energy. I can use any motor for any application. No, it should not be. It should be something like, when you are selecting a motor for a particular application, you have to see the characteristics of the load, and accordingly to you have to select the motor for that particular application. Is this point clear? Confirm me. Confirm me. Right. So this is something about your, while you are selecting the particular loads, right? See, voice breaking from my side. I don't have. What is series motor? One more. What is series motor? You don't know. DC series motor I'm talking, right? Your DC machine teacher will explain. Don't worry, right? DC series motor, your teacher will explain. Don't worry. Fine. So this is something about your types of mechanical loads. I hope this point is clear. All of you confirm me once. Confirm me once. All right. Done. The next one is the torque slip characteristics of a three-phase induction motor, right? So whatever the motor we are talking about, I'm trying to draw, it's a torque versus speed curve. The torque versus speed graph I'm trying to draw now, right? So please learn the torque slip characteristics. Torque slip or speed characteristics of a three-phase induction motor. Three-phase induction motor, right? Now we are going to plot. See what happened. People are raising the hands. You are clear with me? So just please once again confirm all of you are clear with me. See, please explain traction load. Traction is your engine load, right? So what is the load? Maximum at starting, and with the increase in speed, the load on the motor will decrease. Torque slip characteristics, right? See, so I'll take the torque equation. What is the torque equation? Electromagnetic torque is equal to 180 by, see, 1 second, let me disconnect and now finally confirm me once, audio, video and everything, right? Please. So I need to plot the torque versus speed. What is the equation for 180 by 2 pi ns s e2 naught square into r2 by r2 square plus s x2 naught whole square, right? Wait 1 second. Right. So this is the equation for torque for any value of slip ranging from 0 to 1. 0 to 1. Now what I need to do means I need to draw a curve, a graph between the motor torque versus the slip. versus the slip. What do you mean by that? See, we have designed one induction motor with the rotor resistance R2, the leakage reactance X2 naught, poles P, the stator windings connected in star, right? And stator to rotor turns ratio A. And this motor, when it is excited with a fixed voltage at fixed frequency, then this motor, torque, due to the torque, it starts rotating and the speed will try to increase and the slip will try to fall. At starting, what is the value of slip? 1. Once the motor starts rotating, the slip value start falling, the speed will increase. With that, the motor torque value also changes. Now you please try to plot the speed versus torque. That means with the speed, how the torque value will change or how the graph of the torque will look like. I need to plot. So here, what are the variables means? Here the variables are the motor torque and the slip, and all these parameters are fixed. So how the developed torque of a three-phase induction motor varies with the slip, I need to plot now for a given excitation and for a given motor characteristics. Is this point clear? Confirm me. Confirm me. Right. But fortunately or unfortunately, knowingly or unknowingly, if you see power cut, right? Don't worry, we have this UPS, right? So fortunately or unfortunately, let me switch on the fan. Or sometime it is chalega, no problem. Fortunately or unfortunately, knowingly or unknowingly, if you see this torque equation, in this torque equation, we have slip in both numerator as well as in denominator. So if I want to plot the characteristics, if I want to plot the curve between the motor torque and slip, what I'll try to do means I'm trying to divide the torque slip characteristics into 3 regions. And in that 3 regions, we are going to find out what is the relation we have between the motor torque and slip, right? So I'm going to divide this torque slip characteristics slip into 3 regions. What are those 3 regions? One is the low slip regions, the low slip region. The second one is the medium slip region, last one is high slip regions, high slip regions, right? Now let us see what is the relation we are having between the torque and the slip during low slip regions, right? So in low slip regions, what is the meaning of low slip regions? In low slip regions, the rotor speed will be closer to ns. The slip will be approximately equal to 0. R2 by S whole square will be much greater than X2 naught square. From that I can say R2 square will be greater than S X2 naught whole square. And in this case, the motor torque is directly proportional to slip. This was already been proved. Is it clear? Confirm me. This is already proved. Confirm me. Right. Done. Then medium slip operations. What is that? We'll see after high slip. Medium slip operation. Medium slip operations. We'll see what is that. Next one is high slip operations. High slip operations. High slip operations. And you know that in case of high slip operation, the rotor speed will be away from synchronous speed. When the rotor speed is away from synchronous speed, the slip value will increase. When the slip value increases, R2 by S whole square will be falling much lesser to x2 naught square, and in this case the motor torque is inversely proportional to slip. This was already discussed. Is it clear? Is it clear? Confirm me, all of you. Right. Now, basing on this, I'm trying to draw the characteristics and I'll explain the reason also. Please see. So I'm trying to draw the characteristics. Right. So on the y-axis, I'll take the electromagnetic torque in Newton meter, and on x-axis, I'll take speed or I'll take slip. So I'll take here S is equal to 1. S is equal to 1. When S is equal to 1, what is the rotor speed there? 0. Then here I'll take NR is equal to NS. Then what is the slip here? 0. Then you can see in this direction, the slip is increasing. In this direction, the slip is increasing. Increasing. And in this direction, the speed is increasing. Just hold. Speed is increasing. Correct? Is it clear? Confirm me. Right. I'm going to divide the torque slip characteristics into how many regions? 3 regions. What are those 3 regions? Let us see. Low slip regions, medium slip regions, and high slip regions. See, if I'm trying to take 0 to 1 as something like 10 centimeter, let me imagine 0 to 1 as some 10 centimeter. Let me imagine. In this 0 to 10 as a 10 centimeter, that so-called as low slip and medium slip should be around 1 to 1.5 centimeter. The remaining 8.5 centimeter should be for high slip regions. Why? Because you know that the operating range of a slip is less than 10%. Remaining 90% is a non-operating region. So that is the reason you have to draw the low slip and medium slip as something like 1.5, means something like 15%, and the remaining 85% you have to draw for high slip region for while you are drawing the characteristics. Is this point clear? Confirm me. Is this point clear? Confirm me. Why? Because most of the students, they draw wrongly the characteristics. So that's the reason I'm trying to highlight. So please remember that. Then you can see here what is the relation we are having between torque and slip during low slip operation. Torque and slip are directly proportional. So whenever the slip is increasing, what happened to the torque value? Increases. So here the torque will increases linearly. The torque will increases linearly from 0 to maximum. The torque will increases linearly from 0 to maximum, and for that maximum torque value, the slip corresponding, we call it as ST max. And you can see the full load torque, I told you that yesterday, it will be nearly 50% of maximum torque. And this is slip, I call it as SFL. This is the slip corresponding to full load torque. Is this point clear? Confirm me. Here, what is the relation we are having between torque and slip? Torque is directly proportional to slip. The nature of the torque slip characteristics is a straight line. It is a straight line. I hope this is clear. Then during high slip operation, what is the relation we are having between torque and slip? They are inversely proportional. You can see the torque is inversely proportional. You can see with the speed, the torque value is falling, inversely proportional. Inversely proportional. Try to draw rough curve, inversely proportional. So here the torque is inversely proportional to slip, and the nature of this torque slip characteristics is a rectangular hyperbola. Rectangular hyperbola. Hyperbola. I think this is clear. Please confirm me. Is it clear? Then you can see this one is a stable region and this one is a unstable region. Unstable region. The high slip region is a unstable region. I hope this is clear. Now, looking into the characteristics, I need to answer 3 questions. In that, you know few questions already, right? And I'm trying to explain the remaining 2 questions. What are those 3 questions? First one is, why the starting torque is very poor? Why the starting torque is very poor? Why the starting torque is less? First question, already you know. Second question is, why with the increase in speed, electromagnetic torque is increasing. Third point is, why after reaching maximum torque is decreasing. Torque is decreasing. So you can see here, when NR is equal to 0, so we have given a name to the torque. What is that? Starting torque. Why the starting torque is very less compared to this maximum torque value? Why the starting torque is less? Then you can see with the increase in the speed, you can see speed is increasing on x-axis. With the increase in speed, thank God, power has come. With the increase in speed, let me put charging for this iPad. You can see 17%. Just 1 second, I'll put charging. Right, I'm back now. I kept charging, no issue. So what are the questions? Please confirm me once. Raise hands. All of you. Right. So what are the questions I need to answer now? Why the starting torque is less like this? And why with the increase in speed, the torque value is increasing? This we call it as pull-up torque, pull-up torque. And after reaching the maximum value, again, what is the reason that the torque value is decreasing? The torque value is decreasing. We need to answer to these three questions. What is the first question? Why the starting torque of an induction motor is very poor? Second one is, why with the increase in speed, the torque value is increasing? Third, why after reaching the peak value or the maximum value, the torque value is decreasing? We need to answer to these three questions. So if you recall the equation for the electromagnetic torque is equal to the rotor input power by omega s. And rotor input power is equal to 3 E2 naught I2 cos theta 2. Cos theta 2. Now at starting, the rotor current will be very high. At starting, the rotor current will be very high at starting. Why the rotor current will be very high at starting? Why? Because the rotor conductors are stationary. The field is rotating with a speed of ns. The flux cuttings will be maximum. The EMFs will be maximum. The currents will be maximum. So this is maximum. But very unfortunately or fortunately, at starting, the rotor frequency is equal to supply frequency, and this x2 naught is very high, very high, very high. Then this rotor power factor will be very, very poor. It is approximately 0.1, very poor, very poor. So even though the currents are very high, as the rotor power factor is very poor, the active power drawn will be very, very less. As the active power drawn by the rotor is very less, the torque which depends on that will be very, very less. So can I say like this? At starting, the currents are very high, but the power factor of the rotor is very, very poor. As the power factor is very poor, the active power drawn by the rotor will be very less. The torque which depends on this will be very, very less. So that is the reason the starting torque will be very, very less. Is this point clear? Confirm me, all of you. Right. So the starting torque will be very, very less. Now with the increase in speed, increase in speed, what happened to the relative speed between field and conductors? The field is rotating with the speed of ns, and these rotor conductors are approaching that ns. The relative speed decreases, flux cuttings decreases, rotor current decreases. So this I2 starts decreasing, right? But as the relative speed between field and conductor starts decreasing, the rotor frequency starts decreasing, then inductive nature starts decreasing, the rotor power factor will start increasing. So two things are happening with the increase in speed. What are those two things? One is the current starts decreasing, but the power factor will start increasing, right? So it is something like this. I'm having f of x is equal to some x into y. See, the product is xy. So x is increasing and y is decreasing. Then what is the product means? We cannot say, right, increase in decrease. For example, if this increase is dominating this decrease, then obviously the product will be increasing. And if the decrease is dominating the increase, then obviously the product will be decreasing. I hope this point is clear. Confirm me, all of you. Confirm me. See, I'm having two variables, x and y, right? So here x is increasing and y is decreasing. So can I say always the product will be less or the product will be high? We cannot say. Why? Because in this one value is increasing, the other value is decreasing. So when I can say that xy is increasing means if increase is dominating the decrease, then that xy will be increasing. If decrease in y is dominating the increase, that xy will be decreasing. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. I'll repeat. Don't worry. So here, what is happening means in this region, what is happening means, so current is decreasing, but the power factor is increasing. So here, increasing cos theta 2 dominates the decreasing I2. So who is dominating means the power factor is dominating compared to the decrease in I2. So here, if you take this active power PRI, so it is 3 E2 naught, this is constant. So in that, this I2 is decreasing, but obviously what happened to this power factor? Increasing. So who is dominating here? This increase is dominating. As a result, what happened to that? Active power drawn from the source increases. When active power drawn from the source increases, what happened to the torque developed over the motor? Increases. So that is the reason here the torque is pulled up from minimum to maximum. It is pulled up from minimum to maximum. You can see this a torque, we call it as pull up, and here it is reaching the maximum value. So in this region, who is dominating here? The power factor is dominating. Power factor is dominating. As the power factor is increasing and hence the torque developed by the motor is increasing, the power factor is dominating. Is this point clear? Confirm me. Is this point clear? Confirm me. So once again, I repeat, please, this is very important. So in most of the interviews, they'll ask you to explain the torque slip characteristics of a induction motor. They'll ask you. So if anyone questions you, why the starting torque is very poor? Why the starting torque is very poor? Then you are supposed to answer, the electromagnetic torque depends upon the rotor input power. The rotor input power is equal to 3 E2 naught I2 cos theta 2, already have derived that. So here 3 E2 naught are fixed and I2 and cos theta 2 are variables here. At starting, as the rotor speed is 0, the field is rotating with ns. The relative speed between the field and the rotor conductors is ns. The flux cutting the rotor conductors are maximum. The EMF induced in the rotor conductors are maximum. The currents are maximum. So the I2 will be very, very high during starting. But very unfortunately, the torque is not only dependent on I2, it is also dependent on the power factor. So at starting, as the rotor frequencies are equal to the supply frequencies, the rotor circuit is high inductive in nature. The rotor power factor is very, very poor. So that is the reason, even though the currents are high, the power drawn by the rotor is the active power, which is very, very less, and the torque which depends on that will be very, 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 very less. I hope this point is clear. Confirm me. Confirm me. Right. Once the rotor starts rotating, what happened to the relative speed between the field and the rotor conductor? Starts decreasing and the rotor currents will start decreasing. So with the increase in speed, the rotor current starts decreasing. It looks like as the rotor currents are decreasing, the active power I2 is decreasing, the active power should is no. But with the increase in speed, the power factor of the rotor is increasing. So which fellow is dominating there means the power factor will be dominating. As one fellow is decreasing, as the other fellow is increasing, and as this increase is dominating the decrease, so that is the reason the torque of the motor will be increasing. So it is reaching the peak value, right? So the motor is being pulled up to the maximum value, right? I hope this is clear. Confirm me, all of you. Right. Only few. What happened to others? All of you raise the hands. Right. But very unfortunately, after reaching the peak value, after reaching the peak value, after reaching T max, the rotor speed will be very closer to ns. As the rotor speed is very closer to ns, flux cuttings are very less. Flux cuttings are less, very less. EMF falls, or the rotor EMF falls. EMF falls. sharply. Why? Because the flux cuttings are very less, sharply. Then I2 falls sharply, sharply. Then even though this cos theta 2 is increasing, so which fellow is dominating means here, 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 decreasing. I2 dominates, increasing the cos theta 2, cos theta 2, and hence electromagnetic torque start decreasing. Electromagnetic torque starts decreasing. You can see that is the reason the electromagnetic torque starts decreasing. So if I look into this, NR is equal to NS, I'll repeat, don't worry. NR is equal to NS, slip is 0. When slip is 0, flux cuttings are 0, EMF is 0, right? Currents are 0. When currents are 0, then what happened to the torque? It should be 0. Then when flux linkages are 0, inductive nature of the rotor circuit is 0. The circuit is purely resistive. The power factor is 1. So even though the power factor is 1, the current is 0. What happened to the active power drawn from the supply? 0. And the torque developed by the motor will be 0. Like that, the torque will fall drastically. The torque will fall sharply like this, right? So here, 3 points I'll repeat. Please understand 3 points. First one is why the starting torque is very, very poor. The reason why the starting torque is very, very poor means this electromagnetic torque depends upon the rotor active power. This rotor active power depends upon the rotor current and the rotor power factor. At starting, the rotor currents are maximum, but the rotor power factor is very poor, and hence the active power drawn by the rotor will be very, 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 very less, and hence the torque which depends on that will be very less. Is it clear up to here? Confirm me. Confirm me. Right. But once the motor starts rotating, then current starts decreasing, the power factor starts increasing. Which power factor is increasing? The rotor power factor will start increasing. But very unfortunately, which fellow is start dominating means the increase in power factor will be dominating. That is the reason the torque is increasing. After reaching that maximum torque value, then you can see the fall in current is so sharp. So it start dominating the increasing power factor. So this fall in current will be so sharp that it will be falling sharply. Even though the power factor is increasing, the fall in current is dominating the rise in power factor, and hence the active power drawn will start decreasing, and obviously the power factor will be, the torque developed will be decreasing. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right, done. So this is something about your so-called as the torque slip characteristics. In other way I can explain, what is that? When the rotor speed is very closer to ns, when the rotor speed is very closer to ns, the flux cuttings are less, currents are less, leakages are less, the inductive nature is less. Then which nature is good means the resistive nature is dominating, the active power drawn will be increasing. But when you are increasing the load, the speed starts decreasing, the frequency starts increasing, the resistive nature of the circuit starts decreasing. So up to here the torque will increase. But after this, which value will be start dominating means the inductive nature will start dominating. That is the reason the torque will start falling. So like that you can explain. So both the things are correct, right? Confirm me all of you. Confirm me. So this is something about the torque slip characteristics of a three-phase induction motor. So I have not explained only on the basis of equation. If it is on the basis of equation, in low slip operation, torque is directly proportional to draw a straight line. And during high slip operation, torque is inversely proportional to draw a curve like this. Torque slip characteristics over. So it is not my analysis. We have seen why the starting torque is less with the increase in speed, why the torque is increasing after reaching the maximum value, why the torque is falling. We have seen all this case in detail. I hope this is clear. Then the next and very important question is, I'll be answering to this question, why the fan is initially accelerating, after that why the fan is reaching to a fixed speed, after that why there is no further acceleration, why the motor is operating with a fixed speed, right? I'm trying to explain that. So I'm trying to explain steady state operation, steady state operation of a steady state operation of a three-phase induction motor, right? Please. So I'll draw the induction motor characteristics. So already we have seen the induction motor characteristics just now. So this blue color represent the torque slip characteristics of a induction motor. Induction motor. Induction motor, right? Done. Now let us consider this motor is driving a fan load. Driving a fan load. Already you know that fan load comes under which type of load? The load torque whose magnitude varies with square of the speed. So when NR is equal, so this is S is equal to 1. Have drawn wrongly. This is NR is equal to 0. Then you can see at NR is equal to 0, the load torque value is 0. And with the increase in speed, the load torque value is increasing. Right, like this. So this blue color represent the induction motor torque characteristics and this green color represent the load characteristics. Is it clear? Up to here clear? Confirm me. Please understand this. Right. Fine. Are Baba, what happens to other? Please raise the hands. Only few. Nothing special here. Right. I told you that for stable operation, stable operation, when I'm using one terminology for stable operation, the motor should not either accelerate, the motor should not either decelerate. It has to run with a fixed speed. The motor torque and the load torque both should be same. When the motor torque and load torque both are same, then I can say that particular speed is a constant speed, right? Or that speed is a steady state speed, right? When both the torque magnitudes are same, then at that particular speed, I can say the motor will be running stably. That speed we call it as a stable speed. Is this point clear? Confirm? Right. Now you please check. When NR is equal to 0, when NR is equal to 0, the motor torque value and the load torque value both are not same. You can see here at NR is equal to 0, this is the motor torque value, this is the load torque value. Both the values are not same. For example, if I take this is 0, something like it is 30, something like it is 100, if I take, so at NR is equal to 0, what is the value of motor torque? 30, what is the value of load torque? It is 0. So at NR is equal to 0, motor torques and load torque both are not same. When motor torque and both load torques are not same, then NR is equal to 0 is not the stable speed. The motor will either accelerate, the motor will either deaccelerate. There is no question of deaccelerating, it is already stationary. So it has to either accelerate. So can I say at NR is equal to 0, motor torque and the load torque are not same, and hence the motor torque is greater than the load torque, the motor will accelerate. Why? Because which torque is dominating here? The motor torque is dominating the load torque and the motor will accelerate. Why? The motor torque value is more and hence the motor will accelerate. Is this point clear? Accelerate. So the motor accelerate to find the load torque. So when the motor is accelerating, you can see the speed of the motor is increasing. When the speed of the motor is increasing, the load torque value is increasing. At the same time, what happened to this motor torque value is also increasing. Now the speed is increasing, both motor torque values are increasing. increasing, the load torque values are increasing. And during this time, the motor is reaching the so-called as the peak value. Again, it is falling down, falling down. So like this, like this, like this, like this, it is coming here. When the rotor speed is near to ns, then you can see both the torques are becoming same. When the both the torques are becoming same, so whatever the speed the motor is operating, that is a stable speed. Why? Because when nr is, when that speed both the torques are same, as both the torques are same, then the motor will run stably with a speed nr which is closer to ns, with a speed nr which is closer to ns. Is this point clear? Is this point clear? So if you look into this fan, if you look into this fan, why the fan is accelerating means at starting the motor torque value is more compared to the load torque. As the motor torque value is more compared to the load torque, then obviously the motor torque is dominating the load torque. The motor will start accelerating. When the motor starts accelerating, then the speed of the motor is increasing. So with this increase in speed, both the motor torque value will increase, the load torque value is increased. You can see both the torques are increasing. So when the speed is increasing, both the torque values are increasing. At a particular value of speed, you can see both the motor torques and the load torques are becoming same. As the both the torques are becoming same, then I can say at that particular speed, the motor will run stably. So this motor will run stably with a speed nr which is closer to ns. I think this point is clear. Confirm me. Confirm me. Right. So from this we can analyze many point. Now what is that many point means? I told you already, this induction motor never runs with a speed equal to ns. It will not touch ns. Why? Because somebody may have, sir, at least once it will touch. There is no chance that it will touch. It will run with a speed always less than ns. Why? I'll tell. See, what I'll try to do means I'll cut down the blades. I'll cut down the blades. When I cut down the blades, what is the load on the motor? Means the load on the motor is your frictional torques. Frictional torques. So I'll draw roughly. Please see. I'll cut down the blades. When I cut down the blades, the load on the motor is the frictional torques. The frictional torque. What is the frictional torque value? Very, very less. Very, very less. The windage and frictional losses, very, very less. So it is something like this. Very, very less. Very, very less. These are frictional torques. Very, very less. Then up to what speed the motor will accelerate means, so the motor will be accelerating with the torque value is increasing, reaching maximum, falling. At the speeds closer to ns, both the motor torque and those frictional torques are matching each other. Frictional torques are matching each other, and hence the motor will run with a speed closer to ns. So there is no chance that it can touch ns and it come back. There is no chance. Why? Because before to that only the load torque and the motor, the frictional torques are matching, and the motor has to run with the speed closer to ns. I hope this point is clear. Confirm me. Confirm me. So tomorrow, if anyone questions, are your induction motor, is there any chance that it can run at least once with a synchronous speed? There is no chance. There is no chance that the rotor can run with a speed equal to ns. It will run with a speed always less than ns. Why? Because whatever the speed that is less than ns, it is decided by the load on the motor. If the load on the motor is very less, the speed will be very close to ns. If the load on the motor is more, the speed will be little bit away from that ns, but it never be equal to ns. It never runs with a speed equal to ns. I hope this point is clear. Confirm. Right. And one of the student asked me, sir, you told that the induction motor has to be designed with the speeds closer to ns, right? So how to design the speeds? You know that st max is equal to r2 by x2 naught. So this is the slip at maximum torque. For example, say if I'm designing the rotor resistance with low values, when I'm designing the resistance with low values, then that slip will be very closer to 0. Why? Because the R2 is very less, the slip will be very closer to 0. But if I'm designing the motor with high resistance, then the ST max will increase. ST max will increase, like this it will go. When this ST max is increasing, for example, say if the motor is driving the fan load like this, you can see this is operating speed for this, this is operating speed for this, this is operating speed for this, this is operating speed for this. Then you can say this is ns, this is nr. If this is the characteristics, the speed is far away from ns, the flux cuttings will be more, currents will be more, ohmic losses will be more, the temperatures will be high, the machine will be supplying the required load, but the machine will be heating up, it will be very hot, and efficiency of the motor will be very, very less, and the life of the motor will be reduced. So that is the reason we are not supposed to design the motor with these characteristics. Why? Because with that the speed will be far away from that synchronous speed. So we have to design with this. So who decide means the resistance of that winding decide that operating point, whether it should be close or it should be far away. I think this point is clear. Confirm all of you. Confirm all of you. Right. So finally, let me mix up all these things. Let me mix up all these things. So we are drawing the torque slip characteristics of a three-phase induction motor. So if I want to draw the torque slip characteristics of a three-phase induction motor, I have taken the torque equation. In the torque equation, that slip is present in both numerator as well as in denominator to plot the characteristics, to plot the curve. We have divided the torque slip characteristics into three regions: low slip, medium slip, and high slip. And in low slip, the torque is directly proportional to S, and during high slip, the torque is inversely proportional to S. Basing on that, we have drawn the torque slip characteristics of a three-phase induction motor. After that, we have analyzed what is the reason that the starting torque is less, what is the reason that with the increase in the speed, the torque is increasing, what is the reason that after reaching the maximum value, the torque value is decreasing. The reason why the starting torque is very poor means the power factors of the rotor circuit is very poor at starting. Why? Because the rotor frequencies are equal to the supply frequencies, and hence the starting torque will be very less. But with the increase in the speed, as the rotor frequencies are falling, then the inductive nature of the rotor circuit is decreasing, the power factor is increasing, and hence the torque developed by the motor is increasing. But after reaching that peak value, even though the power factor is increasing, the current drawn by the rotor circuit is falling like sharply. Why? Because the speed will be very closer to ns, the speed will fall sharply. The current will fall sharply. That's the reason the active power drawn by the rotor will fall sharply, and hence the torque developed by the motor will fall sharply. At nr is equal to ns, the current will be 0, but the rotor power factor will be 1. But the active power is equal to E2 naught I2 cos theta 2. E2 I2 is 0. Even though the cos theta 2 is 1, the torque developed will be 0 at synchronous speed. Is this point clear? Confirm me. Confirm me. Right. Now we have taken the example of a fan. Why at starting the fan will be initially accelerating, after reaching a peak value or after reaching some speed, it is rotating with some steady state operation. The reason is at starting the motor torque dominates the load torque, the motor will be accelerating, after that it will be continually accelerating, both the torque should become same. Once both are becoming same, then the rotor will run stably with that particular speed. Is it clear? Raise the hands. Right. Then if I cut down the blades, then the rotor speed will be very closer to ns. Then I told you that the manufacturer has to see that the rotor speed should be always closer to ns. So why? Because if rotor speed is falling away from ns, then obviously the relative speed will be high, the flux cuttings will be more, ohmic losses will be more, the temperatures will be more, and windings will get damaged. So for that, we have to design in such a way that the rotor speed should be always closer to ns, the slip should be always closer to 0, or it should be less than 10%. For that, we have to choose the proper values of R2, right? I think this point is clear. Please confirm. Right? Done. I think this is clear. Done. So this is something about the torque slip characteristics of a three-phase induction motor and their analysis. Right? Done. Let us see any questions. After that, I'll go for the next point, next important thing. What about the medium slip operation? Medium slip operation means the torque, already I told you, in medium slip operation, torque and slip are directly proportional. Why? Because Medium slip operation is nothing but overload condition. So there, with the increase in the load, the motor torque will also increases. But in that, the windings will carry very high currents. The relation will be a straight line there, right? Please. How do we, the power factor is dominating? Simply, we have drawn the characteristics with the equations. Torque is inversely proportional to slip and torque is directly proportional to slip. So we have to correlate both the things. So from that, we have to say the power factor is increasing, right? We have to correlate both. Please remember that. Sir, please repeat that power factor is increasing with the speed. Ha, Baba. When the speed of the motor is increasing, then the relative speed between the field and the rotor conductors are decreasing. Then obviously what happened to the frequencies of the rotor currents? Decreasing. When the frequency decreases, the reactance decreases. When the reactance decreases, the power factor will increases. Satish. Sir, how you draw the load torque? Already I have explained the load torque. In case of fan load, the load torque is directly proportional to square of the speed. So it is not like drawn blindly. Already I told you how the power factor is dominating. You have to correlate both the things. Right, done. So this is something about the torque slip characteristics of a three-phase induction motor. The next and very, very important thing is stability analysis. So basing on this, many times we are having a question, stability analysis. Stability analysis. Stability analysis. What is the meaning of stability analysis? I think you might have discussed this in your control system. One second. What is this stability analysis? See, I'll take an example. From that, you can understand what is this stability analysis. See. So this is a bowl, right? So in this bowl, there is one ball, right? So if I'm applying a force like this, a small force like this, a smaller disturbance I'm creating. So because of this disturbance, this ball is moving here and I have removed the disturbances. When I have removed the disturbances, this ball will come and sit again here. So can I say the ball in that bowl is stable or unstable? It is stable. On what basis I'm calling it as a stable means even after the disturbances, then the ball is coming back to its original position. So where it was, again after the disturbances are removed, gone, it is coming back to its original position. Then I can say the ball is stable. Is this point clear? Is this point clear? Right. Then I'll do this. I'll take the same bowl. I'll reverse the bowl like this. And I'll put the ball here. I'll put the ball here. And if I apply a small force here, then obviously this ball will come here. Even if I remove that force, there is no chance that this ball will come back to that previous state or previous position. So here I can say it is unstable and here I can say it is stable. What is the meaning of stable? So if the ball is subjected to some smaller disturbances and if the disturbances are removed, if the ball is coming back to its original position, I can say it is stable. And if the ball is not coming back to its original position, then I can say it is unstable. I hope this point is clear. Confirm me, all of you. Confirm me. Right. So here also with respect to induction machine, how to define stability means, say an induction motor is operating with a particular point, particular speed. At that particular speed, both the torques are same. TEM and TL, both the torques are same. It is operating with a particular speed, right? It is operating. but due to some disturbances, the speed of the motor is either increase or decrease. The speed of the motor is disturbed. There is some disturbances, and the disturbance is removed back, or it is gone. Then after the disturbance is back, then if the point is again coming back, I can say it is a stable point. If the point is not coming back, I can say it is an unstable point. Right? This is the logic which you are supposed to follow. Right? See, the induction motor is operating with some operating point. Now the machine is subjected to some disturbances, and due to the disturbances, the speed is just varied. Because of the variations in the speed, if the speed is not coming back, if the point is not coming back, then I can say it is unstable. If the motor is coming back to its point, I can say it is stable. I hope this is clear. Confirm me, all of you. Right. So I'll be explaining what is that stability analysis. Please go through. You know, these are all important things, right? But you have to learn this. So I'll draw the torque slip characteristics of an induction motor. Let us consider it is a 6-pole motor, right? So this blue color represent the electromagnetic torque characteristics of a 3-phase induction motor, right? Now let us consider this motor is driving a constant torque load. This motor is driving a constant torque load. This motor is driving a constant torque load. So this green color represent the load characteristics. But if you are going to start the motor with this green color, it will not start. Why? Because at starting, this load torque is very high, right? It cannot. It means that the motor is started with very less load and slowly the load on the motor is increased. Right? Somewhere it is operating here now, like this. So how many operating points are existing in this? Now there are 2 operating points. What are those 2 operating points? Operating point A and operating point B. Now among these A and B, I need to find out which one is a stable operating point, which one is an unstable operating point. Even tomorrow in your gate examination or engineering service examination or any compute examination, the motor characteristics will be given, the load characteristics will be given, and some operating points will be given, and you are asked to find out among these operating points which one is a stable operating point, which one is an unstable operating point. You need to identify. Then how to identify the operating point? See, as it is a 6-pole induction motor excited with a 50 hertz supply, 50 hertz supply. What is the synchronous speed here? The synchronous speed is 1000 rpm. Ns is 1000 rpm, right? Now let us consider here the speed of the motor is 950 rpm. Here the speed of the motor is some 500 rpm. Let us consider some 500 rpm. So first I'll check whether point A is stable or unstable, right? Check. Let us check point A is stable or unstable. Right. At point A, as of now, electromagnetic torque is equal to load torque and the speed of the motor is 950 rpm. 950 rpm. So can I say at 950 rpm, both the torques are same here as the both the torques are same here, the motor torque and the load torque are same here, then 950 rpm is a stable operating speed. It can run or it can operate with that speed as of now. Now I need to check whether it is stable or unstable. What is the meaning of stable or unstable? Even after the disturbances has occurred, again if that point A is coming back, then I can say it is stable. If that point A is not coming back, then I can say it is unstable. This example which I took in the previous case, that bowl and ball, right? Please see. So for that, what I'll try to do means, see, I'll create some disturbance. And due to the disturbance, what has happened is the speed of the motor is reduced. So you can see speed of the motor is reduced to say 940 rpm. You can see decrease in speed, you drive to right side. The speed of the motor is reduced to 940 rpm. Then when the speed of the motor is reduced to 940 rpm, then what happened to the torque developed by the motor? Then you can see this electromagnetic torque will increase here. The electromagnetic torque will increase here, but the load on the motor is same. So can I say at 940 rpm, at 940 rpm, 940 rpm, motor torque and the load torque both are not same, and the motor torque is greater than the load torque. Then 940 rpm is not stable. That means it cannot run with 940 rpm. Why? Because both the torques are not stable. As of now, clear, confirm. As of now, clear, confirm. Only few. What happens to others? Raise the hands. Right, done. As it is not stable, then the motor has to either accelerate or the motor has to decelerate. So acceleration and deceleration depends upon the magnitude of the motor torque. If the motor torque is more, compared to the load torque, the motor will accelerate. So here which torque is more means motor torque. As motor torque is dominating, then it will accelerate. So acceleration means from 940, the motor speed will try to increase. Say 941. When the motor speed is increasing to 941, this torque will fall. 942, this will fall. 943, it will fall. Like this, when the speed is increasing, this motor torque is decreasing. A situation will come when motor speed is again 950, both the torques are becoming same. When both the torques are becoming same, then there is no further acceleration. The speed will be stabilized and the motor will run with the speed back to 950 rpm. So can I say if the motor is operating with point A, if the motor is operating with that point A, say because of some disturbances, if the speed of the motor is decreased, if the speed of the motor is reduced, then immediately what happened to the motor torque value? The motor torque value is increased, and this motor torque value is increased. As the motor torque value is increased, the motor is accelerating. Once it starts accelerating, that increase in motor torque value is decreasing. So this acceleration will continue till both the torques are becoming same. Again, the point is coming back to A. That means again it will run with the speed equal to 950 rpm. So the disturbances are reducing the speed to 940. So once the speed has reduced to 940, the motor torque is increasing. The increase in motor torque is accelerating the motor. Again, the speed is reached back to 950 rpm. So as of now, can I say point A is stable or unstable? It is stable. Is this point clear? Confirming. Right. So here the motor will accelerate till 950 rpm, where electromagnetic torque is equal to load torque. I think this point is clear. Confirm me, all of you. Confirm me, all of you. All right. So can I say if the induction motor is operating at on point A, even a small disturbance to decrease the speed, is increasing the motor torque. So the increase in motor torque is accelerating the speed. Again, it is bringing back the speed to 950 RPM. So it is stable. So on only one basis, I cannot say it is stable. Let me check the other case also. What is that other case? So due to the disturbances, the speed of the motor is increase. Increase means towards 1000 you have to go. Increase to 960 RPM. So when the speed of the motor is increased to 960 RPM, what happened to this electromagnetic torque starts decreasing. So due to the disturbances, the speed is increased. When the speed is increased, what happened to the motor torque decreases. So can I say, so due to disturbances, the speed is increased. So at 960 RPM, the motor torque and the load torque both are not same. The electromagnetic torque is less than the load torque. The motor torque is falling less than, then the motor will decelerate. When the motor is decelerating, the speed of the motor will decrease. So the speed of the motor will fall. So from 960, it will decrease to 959. Then this torque will increase. 958, this torque will increase. Like this will decelerate till 950 RPM. Once it is reaching 950 RPM, both the torque will remain same. Again, the motor will run stably with a speed of 950 RPM. So this will decelerate till 950 RPM. Electromagnetic torque is equal to load torque. So can I say, if the motor is operating with point A, even after the disturbances have occurred, then the motor is managing itself by counter its electromagnetic torque. How? Whenever there is a disturbance, to reduce the speed, the motor torque is increasing to accelerate the speed. Whenever the disturbances are increasing the speed, the motor torque is decreasing to decelerate the speed. Like that, the electromagnetic torque is managing to bring back the speed back to 950 RPM. So can I say point A is stable or unstable? So point A is stable as of now. Is this point clear? Confirm me. Point A is stable. So here I'll give a cut short. What does that means? So here, if the motor torque and the speed are inversely proportional, then I can say it is stable point. Otherwise, it is unstable. What do you mean by that? So due to the disturbances, if the speed is increased, if the speed is decreased, the motor torque has to increase. Why? Whenever there is a decrease in speed, the motor torque has to increase to accelerate this. So whenever the disturbances are decreasing the speed, the motor torque has to increase to accelerate that. If this relation is holding good, then that is a stable point. You can see here, due to the disturbances from 950, when the speed is coming to 940, the motor torque is increasing. So due to the decrease in speed, the motor torque is increasing. So it is stable. Second, when the speed is increasing, the motor torque is falling, then it is a stable point. So to check whether the point is stable or unstable, there is no need to do all this groundwork. You see the relation between the motor torque and the speed. So the disturbances are decreasing the speed, you see the motor characteristics. If they are increasing, stable. If the disturbances are increasing the speed, you see the magnitude of the motor torque. If it is decreasing, it is stable. Otherwise, it is unstable. I think this point is clear. Confirm. Right. So this is only for your analysis. Now I'll go for this point B. I need to check whether point B is stable or unstable. Then I'll go for this. Basing on this, I can decide. I'll go for this, right? At point B, as of now, the motor torque and the load torque both are same. What is the rotor speed? 500 RPM. Now say due to the disturbances, the speed of the motor is reduced. The speed of the motor is reduced to 490 RPM. Whenever the speed of the motor is reduced to 490 RPM, you can see when compared to this torque magnitude, this torque is reduced. So decrease in speed is decreasing the torque. Then you can see due to the decrease in speed, the motor torque is decreasing. It is falling less than the load torque. When the motor torque is falling less than the load torque, the motor will still decelerate. Like this, it will decelerate, 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 finally come to standstill position. So point B is stable or unstable here? It is unstable. Why? Because at point B, what is the relation we are having? Motor torque and speed are directly proportional. Due to decrease in speed, the motor torque is decreasing. But whenever the speed is decreased, the motor torque has to increase to accelerate, but it is decreasing. So it is stable or unstable here? It is unstable point. So among these two, which one is a stable point? A. Which one is unstable point means B. So it is unstable and this is stable. This is stable. So tomorrow, whenever such questions are being asked, please try to find out. You decrease the speed, increase the speed. See the characteristics. If the motor torque is increasing when you are decreasing the speed, then it is stable. If the motor torque is decreasing when you are decreasing the speed, it is unstable. Why? Because whenever the speed is decreasing, if the motor torque is decreasing, it will still decelerate the motor and finally it will make the motor to stop. So it is an unstable point. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. So this completes the torque slip characteristics of a three-phase induction motor. So what are the things we have seen? Still it is not over. Still some points are pending. We'll see that also. Don't worry. So what are the things we have seen? How the torque slip, the torque speed curve of a three-phase induction motor looks like. How to plot that curve, how to draw that curve, right? After that, we have seen the steady state speed or steady state operation. That means it doesn't mean that when you are giving a three-phase supply or a single-phase supply to the motor will settle down to its speed like randomly. So it will take some time to to reach to that steady state speed. Why? Because at starting, both the torques may not be same. Definitely the motor torque will be more than the load torque, and the motor will take some time to accelerate to reach to the speed where both the torques are becoming same. When both the torques are becoming same, then the motor will run stably with that particular speed, and we name that speed as a steady state speed or steady state operation, right? Then say if I'm taking the examples of a fan, if I cut down the blades, then the speed will be very closer to ns. Then I told you that the rotor speed has to be always closer to ns. If the rotor speed has to be closer to ns, then the Tmax should be always closer to 0. And for that, the resistance should be very, very less. So if the resistance is very, very less, then the slope will be very less. So this point will be very closer to ns, and the speed of the motor will be very closer to ns from no load to full load. Like that, we have seen that stability analysis also. Is it clear? Confirm me all of you. Confirm me all of you. Right. Then after that, I'll take some break. After that, we'll see the family of torque slip characteristics with a different resistance and different parameters. We'll see that after the break, which is very, very important, right? So we'll see after the break. Right, I'm back. Right. So all of you, please confirm me. You can hear all of you. Right. So the next and very important concept is the family of torque slip characteristics with a different rotor winding resistance. So again, I'll explain a few more points on here. What is it? Next, family of torque slip characteristics with different rotor winding resistances. So what do you mean by that? See, I'm having four resistors R2, R2 dash, R2 double dash, R2 triple dash. So I'm having four induction motors A, B, C, and D. See, these four induction motors are identical motors with only one change is their rotor winding resistance. So these four motors have all similar parameters, only the rotor winding resistances are different. So in this, R2 triple dash is greater than R2 double dash greater than R2 single dash greater than R2. So which motor is having very high resistance means that motor D. Which one is having low resistance means motor A. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. Now, I want to plot the characteristics of these four motors, right? So whatever the point I have explained here, I'll explain this once again. This point once again I'll explain. Please see. See, let us see the parameter which changes with the rotor winding resistance. If you remember, maximum torque is independent of R2. T start is directly proportional to R2. ST max is directly proportional to R2, and NS is independent of R2. Independent of R2. I think all this you know. Please confirm Baba once. Right, done. Now I'm going to plot the characteristics. Zero, right? So which motor is having very low resistance means motor A is having very low resistance. For example, say all the motors are designed for 6 poles and they're excited with 50 hertz supply. All four motors are designed for 6 poles and they're excited with 50 hertz supply. Now let me draw for motor A. So motor A is having very low resistance. As that resistance is very small, then you can see the slip at maximum torque is also very small. Small in the sense it is very closer to zero value. Now let me draw the characteristics for motor A, motor A. I'll draw for motor A, motor A. So let me call it as for motor A. You can see this ST max is very closer to NS. So here what is the value of NS? 1000 RPM. Let me consider. This is very closer to NS. Is this point clear? Why I have drawn that ST max very closer to NS means the value of resistance is very small. Please confirm me all of you this. Right. Then when compared to R2, what about the value of R2 dash? The value of R2 dash is more. So when the value of R2 dash is more, then with respect to motor A, then what will be the changes we can find in motor B? Means as the value of rotor resistance is more than motor A, the starting torque will be more. The slip at which the maximum torque will be increased, but there is no change in the maximum torque. Now let me draw for this is for R2 dash. You can see there is no change in maximum torque, but you can see the starting torque is increased. Is this point clear? Confirm me all of you. Is this point clear? Confirm me all of you. But only few, what happens to others? Please raise the hands all of you. Right, done. Then when compared to your R2, R2 double dash is still more. R2 double dash is still more. Then what will be the characteristics for R2 double dash? You can see this will be far away, and you can see this is R2 double dash. Then what will be that R2 triple dash? It is the resistance due to the resistance of motor D. This is R2 triple dash. You can see here this maximum torque is equal to starting torque. You can see here the maximum torque and the starting torque both are same, right? So these are the torque slip characteristics of four motors with a different rotor winding resistances, keeping all other parameters constant. Is this point clear? Confirm me. Confirm me. Right. So what should be the maximum value of that resistance? Means the maximum value of that resistance should be equal to the standstill leakage reactance. If these two are the same, then that ST max will occur at starting. Then you can see the maximum torque and the starting torque will be same. Now let me analyze. So one question was asked previously by one of the student. What was that question means when I was giving this statement? What is that? If the rotor speed is away from synchronous speed, then the rotor efficiency decreases. Why? Because if you recall that the rotor efficiency is equal to, this is very important point. No textbook will define all these things. Please see. The rotor speed, the rotor efficiency is equal to rotor speed by synchronous speed. If the rotor speed is away from synchronous speed, the rotor efficiency will be less. The overall efficiency will be less. So for that reason, the induction motor should be designed for the speeds always closer to ns. For the speeds always closer to ns. Then I told you that the manufacturer will try to design such that the speed should be always closer to ns. For example, say if I'm having these four motors, then if the characteristics are like this, see, if the induction motor is driving a fan load, what is a fan load? The characteristics of the fan load will be like this. If you just imagine. So if the motor is operating with characteristics A, then the speed could be closer to ns. But if the induction motor is operating with B, the speed will be away from. If the induction motor is operating with motor C, the speed will be still away. Then you can see the motor will be still away. So in all the cases, the motor will run. The motor will run. But in which case the motor will run efficiently means in the first case the motor will run efficiently. Why? Because the rotor speed is always closer to ns. In that the relative speed will be less, flux cuttings will be less, EMFs will be less, currents will be less, ohmic losses will be less, and efficiency will be high. The life of the motor will be high. But if the motor is operating with D, that last motor, then the speed is more, then the relative speed will be more, then the flux cuttings will be more, EMF will be more, currents will be more, ohmic losses will be more, temperatures will be more, efficiency will be less. In all the cases, you can see the motor torques and the load torques are same here. The motor torque and the load torques are same here. But which one is the efficient motor in this case means your induction motor. A is efficient motor. Why? Because the characteristics are such a way that the operating point is very closer to ns. When the operating point is very closer to ns, the rotor efficiency will be more and overall efficiency is also more. I think this point is clear. Confirm me all of you. Confirm me all of you. Right. So this is what one of the student was asking in the previous classes. During that time, I postponed that. This point I'll be explaining in the coming days when the torque slip characteristics has reached. Right. So this is something about the answer for that. Right. Done. The next one is family of. So if you are clear with this, please all of you raise the hands. Raise the hands. Right. Done. Family of torque slip characteristics with different leakage reactance. Different leakage reactance. Transcript. What is that? I'm having three x2 naught, x2 naught dash, x2 naught double dash. So in this x2 naught double dash is much greater than x2 naught dash, much greater than x2 naught, right? So I'm having three motors. In that the constructions are same, only the leakage reactances are different. So each motor is having very low leakage reactance means A followed by B followed by C. So which one is having very high leakage reactance means operating point C. Sorry, motor C. Is it clear? Confirmed? Right. Now what are the parameters which affects? What are the parameters which are affected with this leakage reactance? If you remember, maximum torque is inversely proportional to leakage reactance. Starting torque is inversely proportional to square of leakage reactance. ST max is inversely proportional to leakage reactance, and ns is independent of x2 naught. X2 naught. I think these are the four things. I hope this is clear. Right? Done. So which one is having very low leakage reactance means operating point induction motor A, right? If the leakage reactances are less, then what will be the maximum torque? More. What will be the starting torque? More. What will be the slip at which the maximum torque occur? More. Then NS will be same. Now let me draw for A. This is for X2 naught. You can see this is the maximum torque. And you can see the slip at which the maximum torque occurs is away from the synchronous speed. Why it is away from the synchronous speed? X2 naught is less. ST max is inversely proportional to X2 naught. If it is less, ST max will be away from that NS. Is this point clear? Confirm. Is this point clear? Confirm. Right. Done. The next one is this is X2 naught dash. you can see x2 naught dash is more than x2 naught. When x2 naught is increased, what happened to maximum torque? Decreases. What happened to starting torque? Decreases. But you can see the delta T max is this much, the delta T start is this much. So which reduction is more with the increase in x2 naught is the starting torque. Why? Because this is square of the leakage reactance and this is inversely proportional to leakage reactance. You can see this is the decrease in maximum torque. This is the decrease in starting torque. And you can see the ST max is decreased. Why? Because x2 naught is increased. Then similarly, like this. So these are the family of torque slip characteristics with the different leakage reactances. Is this point clear? Confirm me all of you. Confirm me all of you. Right. So tomorrow in your examination, the question will be like this. The characteristics will be given to you and you are asked to find out these characteristics are for variable resistance, variable reactance, like that. They may give some options and from that you need to pick up. So those characteristics are for which parameter variation. So tomorrow, if these characteristics are given to you and if the question is asked, these characteristics are for variable resistance, option A, option B, variable reactance, option C, variable voltage, option D, variable frequency. Then what should be your answer? It should be variable resistance. Like that you can answer basing on the characteristics. I hope it is clear. Confirm me all of you. Confirm me all of you. Next, family of torque slip characteristics with a different voltages. That means keeping all other parameters constant, if I vary the voltage, how the characteristics of that motor varies. See, you know that maximum torque is directly proportional to V square. All these derivations are being done and ST max is independent of V, right? Let me draw. I'll consider three voltages. First is the rated voltage. After this, very important concept we are going to discuss. Every year in GATE, what I observed since 2013 onwards, there was a 2 marks question from the topic, equivalent circuit. So that equivalent circuit is that much important, right? Please remember that. Once again, I'm repeating that equivalent circuit concept is so that much important. Please see. I'm having V1 which is less than V and I'm having V2 which is greater than V, right? Let me plot now. So let me plot first for this is for V. Right. Then when I'm decreasing the voltage, so V1 is less than V, then what happened to maximum torque? Decreases. What happened to starting torque? Decreases. Let us draw for like this. So these are the family of torque slip characteristics with the different voltages. I hope this is clear. Confirm me all of you. Right. So before we proceed to the next topic, Let me update what is that we have learned as of now. Let me update. Or if anyone questions you, or what is that you have learned as of now? Till now, what is that you have learned? We are comfortable. We have learned all the basic laws, starting with Faraday's law, ending with Lenz's law. The basic laws we have learned. After that, we have seen how to produce a rotating magnetic field, the conditions to produce a rotating magnetic field with the three-phase windings, three-phase currents. And in addition to those conditions, with respect to those three-phase winding, we have seen the theoretical proof also. Then after that, we have learned the conditions to produce a rotating magnetic field with M-phase windings and M-phase currents, two-phase windings and two-phase currents. After that, we have seen the construction of a three-phase induction motor, starting with the selection of frame, construction of a stator core, the types of slots, placing of the windings, the concept of pole formation, the concept of torque production, the types of rotors, their construction, advantages, disadvantages, the comparisons, like that we are completely done with the construction. After that, we have learned the working principle of an induction motor, right? What are those two magnetic field, how the rotor rotates, why the rotor speed will be always less than ns, which makes the rotor to rotate in the same direction as the rotating magnetic field. Like that, the complete concept of working is done. After that, I want to know the performance parameters of an induction motor, starting with the rotor input, rotor output, like torques, like that. So to find out all those things, we have designed or we have developed the equivalent circuit of a rotor. Then using that rotor circuit parameters, we can find out the rotor circuit values, input, output losses, and at the same time, the performance parameters like starting torque, full load torque, maximum torque, like that, we are able to find out. After that, we are able to draw the torque slip characteristics of an induction motor. And why we use this induction motor in most of the applications? Why? Because the motor characteristics and the load characteristics in most of the cases are matching. That's the reason we are using induction motor. Then why are the steady state operation? Why the fan will be slowly increasing its speed? After that, why it is reaching to its steady state value, the steady state speed operation. After that, stability analysis and how the characteristics of a motor varies with the different parameters. We have seen this. Is it clear? Confirm me. Is it clear? Confirm me, all of you. This is what we have learned. The next and very important concept is the equivalent circuit and equivalent circuit analysis. Sir, already you told now equivalent circuit means the electrical circuit representation of a physical induction machine. Of course, yes. Already you have represented the rotor circuit, and using the rotor circuit you have calculated the performance now. Yes. But the thing is, whatever the values we have calculated are approximate values. Why they are called as approximate values means we have not considered the stator circuit parameters. We have not considered the stator impedance. We have not considered the no load current. We have not considered anything with respect to stator side. We have neglected all the stator side parameters. Only we have considered the rotor side, and using that we have calculated the performance parameters. They are only approximate values. Now I want to find out the exact values. So if I want to find out the exact values, then what I need to do means I need to develop the complete equivalent circuit of an induction motor. Now I'm trying to build up the complete equivalent circuit of an induction motor. With this complete equivalent circuit, we are going to find out the exact steady state analysis, exact values of full load torque, maximum torque, starting torque, like that we are going to find out. I hope you understood the difference between complete equivalent circuit and rotor equivalent circuit. Using rotor equivalent circuit, we can find out only the approximate value, and using the complete equivalent circuit, we can find out the exact values, right? I hope this is clear. Confirm me, all of you. Confirm me, all of you. Right. So let me go for the complete equivalent circuit of the complete equivalent circuit of a of a three-phase induction motor. By the way, what is an equivalent circuit? An equivalent circuit, an equivalent circuit is electrical circuit representation of complete induction motor. Right? Done. Now let me build up the complete equivalent circuit, right? Already we have seen the rotor circuit. So let me build up. So here, what is that R2 represent in the rotor circuit? R2 represent the rotor winding resistance, and it is accountable for the ohmic losses in the rotor winding. If you recall the construction wise, any motor is two electromagnets. So when we are talking about the rotor core, the rotor windings. So whenever that winding carries current, there will be some loss, and that loss, if you want to calculate, that is accounted with the rotor winding resistance. Similarly, in the stator also we have core, and in the core we make slots, and in the slots we place windings. So whenever those stator windings are carrying current, so there will be some loss, and that loss we are accounting with that stator winding resistance. So what is this stator winding resistance? We represent R1. So if anyone asks, what is that R1 represent? It represents the stator winding resistance. So for what purpose we are using that stator winding resistance? It is accountable for the ohmic losses in the stator winding. So if anyone gives the values of R1 and the value of I1, and if they ask you to find out the stator ohmic losses or the stator copper losses, just like your rotor copper losses, you calculate 3I2 square into R2, the stator copper losses can be calculated like 3I1 square into R1. I think this is clear. Confirm me. Correct. Again, it is a series branch. Similarly, the winding inductance and the leakages is accounted with a leakage reactance. You know what is the importance of that leakage reactance. Again, I'm not going to explain that. That was already explained. Similarly, we are having the leakages in the stator circuit also. Done. In case of your rotor, the rotor core losses are neglected, right? The rotor core losses are neglected. That is the reason we are not showing any branch which is accountable for rotor core losses. But whereas in case of stator, the core losses are not neglected. Why? Because the stator core frequencies are always equal to the supply frequencies. Those core losses cannot be neglected. So to account that, we are measuring, or we are representing one more branch, that is the core loss branch. That is the stator core losses. Now the question comes, sir, why you are representing this winding resistance as a series branch, and why you are representing this core losses as a shunt branch? The simple thing. So in winding, there will be loss when they carry current. When there is no current, the losses in that windings will be zero. So the losses in the windings depends upon current, and that current is a series parameter. That is the reason we are representing that R1 as a series branch. I think this is clear. Confirm me all of you. But whereas the core losses, they are not dependent on current. The core losses depends upon voltage. I think in your transformers you might have seen, else you'll see, don't worry. Those core losses depends upon voltage, so they are not depending on the current. So even the motor is carrying full load current, no load current, X current, Y current, so they are not bothered about the current. That depends upon the voltage V. So whenever you are applying a voltage V, then the losses will be rated losses. So as there depends upon the voltage, so voltage is a shunt branch elements or a series branch elements means it is a shunt branch element. That is the reason we are representing like a shunt branch elements here like this. So this is a shunt branch elements like this. So two things to be noted here. The winding losses we are showing like a series branch. R1 we are showing it as a series. Why? Because it depends upon the current flowing in the winding. When there is no current, when the motor is not loaded, then the winding losses will be zero. So that is the reason I'm showing like a series branch. But this core losses that doesn't depends upon the current, that depends upon the voltage. And you know that voltage is a shunt branch parameter. That is the reason we are showing that core loss branch as a shunt branch. Is it clear? Confirm. Right. The next one is the permeability of the core. Whatever the core we are taking, the permeability of the core is not infinite. The permeability of the core is not infinite. If the permeability of the core is infinite, then obviously the magnetizing current will be zero. But it is not infinite, it is only finite. So account that we are representing one more branch, the magnetizing branch Jx, which is accountable for a finite permeability. Why? Because you know that the Ampere circuital law. What is that Ampere circuital law? So if you want to produce a magnetic field, then I need a magnetizing current. So the magnetic field intensity around a closed path is equal to the current enclosed. So if I take the magnitude H into L is equal to I mu, and if I write B by mu into L is equal to I mu. If the permeability of the core is infinity, then the required magnetizing current to set up the core will be zero. But very unfortunately, if you see the magnetic circuit of an induction motor, this is the magnetic circuit of an induction motor like this. So this is your stator winding, let me assume. The magnetic circuit of an induction motor is not having infinite permeability, right? Why? Because due to the presence of air gap, there is no infinite permeability. The permeability of that magnetic circuit will be only finite. When it is finite, definitely it will draw some magnetizing current. So in order to show that magnetizing branch, we are showing this XM. For example, if the permeability of that path is infinite, then that magnetizing current will be zero and that branch will be shown as an open circuit. But here the magnetizing current is not zero. That is the reason I'm showing that branch. I think this is clear. Confirm me. Confirm me. Right. Then here I'll be drawing this. And I'm short circuiting this. Short circuiting this. So this is the complete equivalent circuit of a induction motor. Now we can have many points to discuss here. First, number point one, listen. Why in the rotor circuit, this is the rotor circuit, why in the rotor circuit there are no shunt branches, right? There are no shunt branches. What is the meaning of shunt branches? Why there is no RC? Why there is no XM? Two questions. As I told you that the frequency of the rotor currents during running conditions will be very less. The core losses which depends on that will be very less. So that is the reason in all our power stages, in all the power calculations, we are not counting the rotor core losses. The rotor core losses are treated as zero. So that is the reason we are not showing that shunt branch in the rotor circuit. I think this point is clear. Confirm me. Confirm me. Right. Sir, we agree that as the core losses in the rotor circuit are neglected, that is the reason you are not showing any RC, the core loss component in the so-called as rotor circuit. We agree with that. Done. Then why you are not showing any magnetizing current in the rotor circuit? Why? Because even the rotor also carries winding and that windings will carry current. So you have to show some magnetizing current in the rotor circuit. Why you are not showing the magnetizing current in the rotor circuit? The answer for this is, this machine is a single excited machine or a double excited machine. This is a single excited machine. So whatever the magnetizing current that is required to produce the field in both rotor and stator will be drawn only from only one source. Which source? It is the stator source. right? So this source is supplying the magnetizing current to produce the magnetic field. So only this source is supplying, the stator side it is supplying. As it is a single excited machine, we are showing that magnetizing branch only on one side. That is the reason we are not showing on the other side. Say for this is double excited. It is separately excited on the rotor side also. Then I have to show the magnetizing current on the other side also. But as it is a single excited machine, I'm showing that magnetizing branch only on stator side, not on rotor side. As it is a single excited machine, I'm showing only on stator side, but not on rotor side. I think this point is clear. Confirm me. Right. The next question is, sir, why you are showing this? Why you are showing this shunt branches? These shunt branches after this stator impedance. After the stator impedance. Why can't you show the shunt branches before to this? Why you are showing after to this? Very good. So that may be the concept. That may be the question. What do you mean by that? See, I can draw like this. Just roughly I'm drawing. Why can't you show like this? Why can't you show the shunt branches across the source? Why you are showing those shunt branches after the series impedance? Very good. So if you just recall the power flow in transformer, I'm talking about in transformer before to this induction. So first we are giving a electrical power which is in electrical domain. That electrical domain is converted into magnetic domain. That magnetic domain is converted into again electrical domain, right? So here if you just go back to the transformer, whatever that electrical power we are giving, that is not directly converted to magnetic domain. After some losses in the winding, then the remaining power is converted to magnetic domain. After that it is converted into electrical domain. After some losses in the circuit, the remaining power will goes to the load. Once again, if I take a transformer, we are giving some electrical power. Initially the power is in electrical domain. It is not directly converted into magnetic domain. Some losses will be there in the circuit. After that losses, it is converted into magnetic domain. After that, it is converted back to electrical domain. I hope this point is clear. Confirm all of you. So even in induction motor also, so there is a conversion, electrical to magnetic, magnetic back to electrical, electrical to finally mechanical. So before this electrical domain is converted into magnetic domain, there is some loss. There is some loss in the winding. After that loss, there is a magnetic domain. You can see before this electrical power is converted into magnetic domain, there has to be some loss. So that is the reason those loss branches are shown before the conversion into magnetic domain. Then the core losses are taking in the magnetic field. So before the core losses, the losses are taking in the winding. After that, the losses are taking in the core. Why? Because the core losses are in magnetic domain. So that magnetic domain will be after electrical domain. Electrical domain, losses, magnetic domain, losses in the magnetic domain, again electrical, losses, then it is converted into mechanical power. So the losses in the magnetic domain will come after the losses in the electrical domain. So first losses in the electrical domain, after that losses in the magnetic domain. So this RC is the losses in magnetic domain. It should be after the losses in electrical domain. That is the reason I'm showing it as after R1, but not before R1. I hope this point is clear. Confirm me. Right. So these are the points which we are supposed to discuss with respect to equivalent circuit. Oh, that is gone. No problem. We can bring back. Right. So this is something about your equivalent circuit of a induction motor. So please remember, you don't draw two lines here. If you're drawing two lines, so the media is something like, what is that media? You don't draw two lines here. So here the media is not the core, right? So in between the stator magnetic field and the rotor magnetic field, there is no core. The media is here air. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. So this is something about your so-called as the equivalent circuit, right? Right. Once again, I'll repeat. So see, what is that R1 represent? R1 represent the ohmic losses in the stator winding. Generally, R1 is the stator winding resistance and it is accountable for the ohmic losses in the stator winding. And you know that in addition to that losses in the winding, even in the losses will be there in the core. So whenever we are talking about loss, we have to represent it with a resistor. So the losses in the winding is represented with R1, the losses in the core is represented with a RC. Why we are showing that R1 has a series branch means it depends upon current, the load current, whereas the core losses depends upon voltage. That's the reason we are representing it like a shunt branch. Is it clear up to here? Confirm me all of you. All right. So what is that XM? XM is the magnetizing current. That means as you can see the magnetic circuit of an induction motor is discontinuous. The permeability of that path is not infinite. The permeability of the path is finite. So definitely the machine will draw some magnetizing current even though there is no load. It will draw some magnetizing current to produce a flux. So in order to show that magnetizing that flux, I need to show one branch. That branch is nothing but magnetizing branch. Why? Because the coil which produces a magnetic field that I'm showing like a magnetizing branch. I think this point is clear. Confirm me. Confirm me. Now the question comes, why we are not showing these branches on the rotor side? Why we are showing these branches only on stator side? Why? Because it is a single excited machine. So whatever the reactive power that is required to produce the field will be drawn only from the stator side. That's the reason I'm showing only on stator side. Say for example, if you're exciting both stator side as well as the rotor side, then you have to show that magnetizing branch on the rotor side also. Why? Because it is double excited, but it is only a single excited here. Clear? Confirm me. Confirm me. Then why that R1 is before RC? Why can't be it is after? Means this R1 is the losses in the electrical domain and RC is the losses in the magnetic domain. So before the electrical domain is converted into magnetic domain, there should be some loss in that electrical domain. That's the reason it is shown before to the magnetic domain, not it is after to the magnetic domain. I hope this point is clear. Confirm me all of you. Confirm me all of it is clear. Right, done. Now I need to find out the performance parameters. So what are those performance parameters means? Again, the same logic, same logic. So if I want to find out the performance parameters of an induction motor, if you recall the rotor circuit, what are the things given? R2, X2 naught, E2 naught are given. Using these three values, R2, E2 naught, X2 naught, I can tell the complete behavior of the motor when it is operating at a slip. Yes. Is this point clear? Confirm me. Confirm me. So now, if I want to find out the total exact performance of this induction motor, in addition to this, all the equivalent circuit parameters R1, X1, R2, X2, RC, XM, V1 are given. So all these parameters are given and you want to find out the performance parameter of an induction motor when it is operating at a slip. Yes. At a slip. Yes. At a slip. Yes. Is this point clear? Confirm me. Is this point clear? Confirm me. If I want to calculate, yes. If you recall previously, what is that I need? I2. Correct? If I know I2, from that I2, I can calculate rotor input. I can calculate rotor losses. I can calculate rotor output. Even I can calculate torque. Even I can calculate torque. Is this point clear? Confirm me. Is this point clear? Confirm me. I'm correlating, right? I can calculate torque. So what does this I2 means? This is the current that is flowing in the rotor circuit. I need I2. Now forget that this is the equivalent circuit of an induction motor. Assume that it is a simple electric circuit, right? So can you please tell me how to find out I2? How to find out I2? How to find out I2? See, Baba, I'm just assuming that it is a simple electric circuit. I strongly believe that you are good in electric circuit. I'm giving this like this. What is it? 1 ohm, J2 ohm, some 1000 ohm, some J 500 ohm, 1 ohm, J 2 ohm, 100, 200. The turns ratio 100 to 100 is given. Nothing else is given. And this is 100 volts per phase is given. Right? So this is the thing that is given to you. Forget that this is a induction motor equivalent circuit. It is a simple electric circuit. I'm just asking you, can you please calculate I2 here? I2 here. So forget that it is an induction motor equivalent circuit. It is a simple electric circuit, R and L branches. Now these are the things given. Only these things are given to you. Now tell me how to calculate I2. How to calculate I2? Let me see how many will answer. We'll see. See, I'm not that much strong as you are in circuits. So just I want to know how far you know about circuits. See, applying KVL. By turns ratio, transferring the secondary to primary, refer rotor circuit, we can calculate I2. I2 is equal to E2 by Z2. But where is the value of E2? E2 I don't know. I don't know E2, right? Referring the other side, current division rule, no, right? So most of the student told that referring the circuit from one to another, right? Voltage across shunt branch is also don't know. So E1 is also no. So can I finally conclude like this? Can I finally conclude like this? As of now, see, it is enough. Don't throw. KVL and KCLs are not possible, Papa, right? As of now, it is not possible. It is not possible to calculate the value of I2 because of this so-called as transformer presence. Transformer presence. So if I want to calculate the value of I2, then what I need to do means I need to refer all the secondary side parameters to primary side. If I refer all the secondary side parameters to primary side, then I can remove this transformer branch, and without any difficulty, I can calculate the value of I2. Definitely, I can calculate I2. So tomorrow in your gate examination, if the same question is asked, calculate the value of I2 means the procedure which I'm trying to explain, you have to use that, right? So we'll be doing that. I think this point is clear. Confirm me, all of you. Confirm me, all of you. So once again, I'm repeating, please. Once again, I'm repeating. So here, right. So if the rotor circuit parameters are given, what are the rotor circuit parameters are given? So here, if these parameters are given to you, if you want to calculate all these things, then what is required for you? I2. If you know I2, I can calculate input power, rotor output power, losses, the torque, everything I can find out, right? Similarly, if I'm having the complete equivalent circuit, and if I want to calculate the exact values, so what is that required to me is I2. But very unfortunately, for this circuit, calculating I2 is very difficult due to the presence of transformer. So to reduce the complexity, the complications in calculating I2, we are referring all the rotor circuit parameters to state side. To to find out the performance parameters, we need the value of I2. But for this circuit, for the circuit shown above, shown above, it is difficult, it is difficult to calculate I2 due to the presence of transformer. to reduce the complexity in calculating I2, the rotor circuit is referred to stator side. I think this point is clear. Confirm all of you. Right. So we'll see this in the next class. See, before we go for this doubt sessions, tomorrow is a holiday for all the branches, right? Old batches, new batches, X, Y, Z, all the batches. Tomorrow is a holiday. And you know the reason why tomorrow is declared as a holiday. There is no need to reveal. There is no need to tell the reason. So again, our class will resume on Monday, right? So from Monday, I'll be having 5 to 9, the theory, followed by the doubt session. Please try to understand, right? So tomorrow is a holiday. Please try to note this point, right? Done. I'll stop for today. So is it clear? Tomorrow is holiday. Please confirm, all of raise the hands. All right. So the class is not yet over. We need to discuss the doubts. After that, the class will be over, right? Why? Because the key stage is the doubt discussion, right? I'll come back. Just wait. I'll bring the earphones. 1 second. I'm back. First, let me see the question and answers. After that, we'll come back. See, this is a meaningless question. Could you please tell me why rotor core losses are neglected? 1 lakh time I told till now. Please refer the notes. Why holiday? Right. So no technical questions. Let me see. So no one is raising the hands. Right. Imtiaz Pasha.
Good evening, sir.
Good evening, Imtiaz.
Sir,
Yeah.
hello. Sir, I have doubt in the darkest constant you said, no, sir, in the mechanical load.
That is one of the mechanical load. Yeah. What is your question? Yeah, please ask. I'm there. Hmm.
Sir,
Mm-hmm.
for
Example
sir,
is example is lift.
lift. For the squirrel cage induction motor, we start the motor with a load to up to higher load, no, sir. But in lift, we are using constant load, means at that time we can step the 10 members at a time, no, sir.
See, for example, you take a lift with the two persons, okay,
Okay.
which is designed for two persons, okay.
Okay.
So whatever the squirrel gauge induction motor I'm using in that lift application, at starting, it should have the capacity to drive two persons, minimum 0%. So the motor can rotate even with a 0% or even with 2%. Unfortunately, if a third person is taking the lift, the motor doesn't have the capacity to drive. That is the reason, if you look into the lifts, you can see maximum 600 kgs or maximum 10%. Why? Because whatever the motor I am using in that particular case has the capacity to drive at starting up to how much? It is 10 kgs. Understood? So
Yes, sir.
if I try to draw the torque slip characteristics of a squirrel gauge, it is like this. Understood? You can
Yes.
see it. Can you see it on the board? Let me draw. Right. Let me draw with the white color. So these are the torque slip characteristics of a squirrel gauge. Let me show. So
Okay.
this is designed in such a way that maximum what is the load it can carry at starting with the 2%. With the 2%.
Okay,
Right?
sir.
So it will, you can say here, it is developing a torque of how much? 2%. So it will start, and from where it will rotate, it will operate like this. Understood?
Yes, sir. Sir, if anyone ask about that, which
Mm.
motor you are using lift mean, we can say squirrel gauge motor or slip ring motor mostly.
It is a squirrel gauge. For example,
Always.
if you are designing for example, say if you are having a lift, and in that lift there are say 10%. So I cannot use this motor with a 10%. Why? Because the starting torque is only to carry how much? 2%. In that case,
2%.
what I need to do means I have to remove that motor of low HP, and I have to use a higher HP motor which has a capacity to drive 10%. So I'll be having another motor with 10%. So that motor can carry 10%. So if I'm having a lift with a 15%, then I use another motor which can carry 15%. So basing on the capacity of the load, we'll be using the motors there. Right? We are using a squirrel gauge only. Why? Because what is the role of a slip ring? If you want to have high starting torque, then you need a slip ring. But whereas in case of cage rotor, the torque can be constant or the torque can be raising. In both the cases, we can use squirrel gauge induction motors. Understood?
Okay, sir.
Uh,
Mm, it is starting. You said no, sir. Squirrel gauge induction motor. We can't use it. It is starting higher load, no, sir.
Baba, I said we cannot use higher loads. But I told you that whatever the motor we are using in that particular lift application should have a starting torque to carry maximum 2%.
Okay,
If
sir.
the persons are more than 2, the motor torque is not enough to drive that more than 2%. That is the reason the lift cannot move. Even if there are no persons, then the motor can move. 1% the motor can move. 2% the motor can move. Why? Because the starting torque of that motor is to carry up to how much? 2%. If a third person is taking the lift at starting, then the motor cannot move. Why? Because the starting torque is not enough to drive that load.
Yes,
In
sir.
that case, you have to use another motor whose starting torque has the capacity to drive 3%. So like that, basing on the number of persons in the lift, we use the different types of motors, right? So we should
Yes,
not use the slip ring there. Slip ring concept is totally different. What is the meaning of slip ring? At starting, the load is more, then you have to use. But here, at starting or running, the load is same. So we cannot keep that
yes, sir.
resistance, right? Understood?
Yes, sir. Sir, one more door.
Mm.
Sir, in our household fan is there, no, sir.
Mm.
We are using regulator. It
Controller.
means we are adding resistance.
Mm.
if we add
Yeah.
the resistance, sir,
Yeah, I can hear you, Imtiaz Bhai. I can hear.
if if you add the resistance, the flux cutting will be more, the power action will be more. No, sir.
What is the relation between the resistance and that flux cutting? In case of your,
Sir,
please tell.
is it we are adding resistance? Is can be treated as a rotor resistance?
No, it is something like it is a stator resistance. So when you are adding resistance, what is the logic means? Say you are giving 100 watts of power. Say with 100 watts of power, the speed is nearly 1000 RPM. If you want to reduce the speed, then you need to control the power that is being fed to the motor. You are wasting some of the power in the regulator. So that is the reason if you touch that regulator, previous old Dabba regulator, you can see that regulator will be heating up. Why? Because a
Okay.
part of the power is wasted there, the remaining power is fed to that load. But nowadays, those regulators are replaced with a triax. So there is no like wastage of power. So we are controlling the power and we are controlling the speed. That we'll see in the coming days. Don't worry. Don't link up that now. Understood?
Okay, sir. In slip torque characteristic at the point B, no, sir.
Hmm.
Sir, is means you are taking the relation torque is proportional to the n in at the
Yeah.
point of A. You are taking torque inverse proportional to n.
I am not taking the torque is directly proportional to n or inversely. In that case, the torque is inversely proportional to n only. I mean to say that if you want to judge that point is stable or unstable, you see due to the disturbances, if the torque is increasing or decreasing. Due to the disturbances, if the speed is decreasing, if the motor torque is increasing, then that point can be stable. Due to the disturbances, if the motor torque is decreasing, then that point will be unstable. It is not the relation. I told you clearly. Due to the disturbances, if the speed is decreasing, if the motor torque is increasing, stable. Due to the disturbances, if the speed is decreasing, motor torque is also decreasing, then it is unstable. Please keep that in mind. Don't
Okay,
link to
sir.
that.
Okay.
Understood?
Yes, sir. Sir, in last node, sir.
Yeah, please ask.
Sir, in the complete equivalent circuit three-phase induction motor last is there, no, sir.
Hmm.
Can we said that the shunt element is why you are taking shunt means the core loss is always constant. That's why we are using the shunt element.
You are not supposed to say why core losses are always constant. Why? Because the applied voltage is always constant.
Okay, sir. Okay, sir.
If you are varying the voltage, the core losses will change. Old core losses are voltage dependent, ohmic losses are current dependent.
Okay,
Understood?
sir. Yes, sir. I got.
Right. Okay.
Thank you, sir.
Right. Right. Anusha. 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 I think. Where is Sai Charan Reddy today? He's not there. Sarath. Yeah, Sai Charan Reddy. I'm waiting for you. Sharath.
Yeah. Sir, it's a practical doubt, sir.
Yeah, you can ask any doubt.
Actually, sir, actually, for household, we are getting single phase supply.
It is a single phase 230 volts.
But actually, we are saying that line to line voltage is 230 to 240 volt.
See, whenever we talk about line to line voltage, it is with respect to three phase. We don't talk with respect to single phase. Always with respect to single phase, we talk phase to neutral voltage. Right? There is no
Yes, sir.
concept of line to line. It is phase to neutral voltage. Yes, what is your
Okay,
question?
sir. But for single phase induction motor, the supply is 230 volts, no, sir.
Obviously, the supply is 230 volts. What do you want?
But actually, this is phase voltage, no, sir.
For single phase, it is a phase voltage only. For three phase, it is a
Phase
three phase line voltages. What is your question?
phase voltage is 230 volts, 230 volts, sir. Or
See, Baba.
Hello.
Baba, listen. When I'm talking about a three-phase induction motor, the given voltages are always line, right? It is line-to-line voltage. But when we are talking about single phase, the given voltages are phase to neutral. It is a phase voltage, right? The voltages are clear.
Yes.
Now, what is your question with respect to voltages?
There we are getting in three phase we are getting phase voltage as 230 by root 3. No, sir.
See, in case of single phase, for example, if the line-to-line voltage is 230 volts, and if the windings are connected in star, then the per phase voltage will be 230 by root 3. Understood? In
Yes.
case of your single phase, if the given voltage is 230, then per phase voltage is 230 only. What is your question, Sharath? Chelu?
A small confusion, sir. There in three phase we are getting phase voltage as 230 by root 3. No, sir.
See, whatever the numerical I have given, in that numerical, hello, you can hear me, Sharath?
Yes. Yes. Yes, sir.
Right. In that numerical, just to test you how far you are strong in the basics, to confuse you, he has given as a 240 volts three phase voltage. I told you clearly. But generally, it will be a 400 volts line voltage will be given generally. But there is
Yes,
no like a thumb rule that there is no like a IEEE rule that always in the numerical a 400 volts has to be given. But when we are talking in practical, the voltage what we need to apply is a 400. But in numerical, just to know how much you learn about the subject, to test you know how much you know this about the subject, he has given just to confuse you 240 volts, right? So that 240 volts according to that numerical is a line voltage. But in all our calculations, we need phase. That's the reason we have gone for phase. Now we are clear, Sharath?
yes, yes, sir. Yes, sir. Got it,
But,
sir.
right, Bob.
Sir, another doubt, sir.
Hmm.
Sir, where in Tmax the x2 naught is inversely proportional.
Tmax is inversely proportional to x2
Why?
naught.
You,
Why?
you said that we cannot change the x2 naught.
I did. Baba, Sharath, you be clear with your
Sir.
question. I can hear you. You please be clear with your question. I can
Yes,
answer to your question if you are clear with the question.
Yes, sir.
Hmm.
Yes, sir. You said no, sir. X2 naught is fixed.
Yes.
While in manufacturing.
Yeah. Why? What is that X2 naught means? It is the rotor standstill leakage reactance. So it is a reactance offered by the rotor at standstill. So it is not a variable, right? So that value is a fixed value.
Yes, sir. But at starting, X2 naught is more, no, sir.
It is
Compared
more.
to running.
It is more. But during running, what happened to the rotor leakage reactance from X2 naught? It will start decreasing. So from maximum, it starts minimum.
There, X2 naught is variable, no, sir. After designing.
X2 naught is not variable. X2 is variable. X2 is equal to S into X2 naught. So when S is equal to 1, what is the value of rotor leakage reactance? It is equal to X2 naught. Once the motor starts rotating, what happened to this X2 value? It will start decreasing. X2 naught is not changing. X2 is changing.
Got it, sir.
Right. Okay.
Thank you, sir. That's it.
Right, Baba. Right. Right. Sai Charan Reddy.
Hello, sir. Sir, in torque relations, 9th point, sir.
Yeah, just 1 second. Let me open this. Yeah, I'm here. Yeah, please. Yeah, please, Baba.
Sir,
you can
here
see.
after this electromagnetic, sir. After this, sir.
This one. This one.
Sir, yes, sir. This is full load torque. Sir, here you neglected S into X to naught. So we can say that this is also operating in low slip region, sir. Full load torque. We got full load torque in low slip region.
See, let me finish my statement. See,
Okay, sir.
I told you that the complete range of slip for an induction motor is 0 to 1 per unit or 0 to 100%. Is it clear?
Yes, sir.
Right. But in that, what is the operating range? Means it is less than 10%. That means
Yes.
operating range means before the motor stops. That we call it as operating range. It is less than 10%. Is this point clear?
Yes, sir.
Less than 10% means we are calling it as a low slip operations or high slip operations.
Low slip
Low
operation.
slip op. So for low slip operation, instead of using the complete torque equation 180 by 2 pi ns SE2 naught square into R2 by R2 square plus SX2 naught, you can use this torque equation. Which equation? 180 by 2 pi ns SE2 naught square by R2. Why? Because whatever the value we get with that equation, whatever the value we get this equation will be less same. Why? Because in low slip operations, when compared to your R2 square, that Sx2 naught whole square will be less. So that is the reason when we have considered that X2 naught, when we have calculated the full load torque, the numerical was for 52.38. But if I neglect that and if I calculate the full load torque, the answer is 56. Answers are very close, I mean to say. So tomorrow in your examination, if X2 naught is not given and you are asked to calculate full load torque, then don't get confused. Our sir told that for full load torque, the equation is 180 by 2 pi ns SFL E2 naught square into R2 by R2 square plus SFL into X2 naught. So there is no value of X2 naught. The data is incomplete. So I cannot do. So in that case, you can use this formula even to calculate full load torque, I mean to say. Now you are clear with that answer,
Yes, sir. Clear, sir.
right? Done. Still any questions?
Sir, yesterday when I asked about that, if a TM is less than T load, then it is unstable. I asked that one.
If the motor torque is unable to supply the load torque, then the motor cannot rotate.
Yes, sir. That one I clarified today here in that
You got
relation, the torque shift relation.
you got it, right?
Yes, sir. Yes, sir.
You're clear with the doubt, right?
Yes, sir. Yes, sir.
Any more doubt, Sacharan Reddy?
No, sir.
Right. Okay. Gaurav. Gaurav.
Yes, sir.
Baba. Please raise your doubt.
Sir, I have doubt in stability analysis.
Yeah, definitely. I'll move to that point. You can ask any question on stability. This one. Yeah, please.
Mm, Yes, sir. At point A, this if speed there is disturbance after it comes at a point, there it is stable. But I
Yes.
have a doubt about how the acceleration and deceleration takes place.
See.
How it is?
Shall I?
Yes, sir.
Yeah.
Yes.
Yeah. Due to the disturbances, say the speed of the motor is reduced to 940 RPM. Right. This is what I
Yes.
took initially. Right. So
Yes.
just 1 second. 940 RPM. Correct.
Yes, sir.
When the speed of the motor is reduced to 940 RPM, very immediately what happened to the motor torque? So from this point, the motor torque has reached to this point.
Yes.
Correct?
Sir,
Yes.
why it is decelerated down to a point?
See.
The
Now
starting, the torque is rising towards. Okay.
See, it is not rising. When the speed of the motor is 940, the magnitude of the motor torque will be this much. It has raised. You calculate, the motor torque will be increased. But understood?
Okay, sir. Yes.
It is increased. But at that instant, what value of load torque? This is the only value of load torque, correct? So
Yes,
here
sir.
the motor torque and the load torque both are not same. Correct?
Okay,
Correct?
sir. Yes.
So which torque is dominating here? Motor torque is dominating, correct?
Sir. Yes, sir.
When the motor torque is dominating, then what happened to the rotor now? Accelerate or deaccelerate?
Sir, it will deaccelerate.
Or a motor torque is more. See, you are having a 1 kg weight you want to carry and you are having more energy. So you run fast or you run slow
Sir, slow.
when compared to 100 kg weight.
Sir, if weight is less, I will run fast.
Yeah. So here the motor torque is more compared to which torque?
Load torque.
Look. So which torque is dominating? Which torque is dominating? I look the board
Motor
and
torque is.
dominating, correct?
Yes, sir.
When the motor torque is dominating, the driving force is dominating, then it will accelerate or deaccelerate.
It will. Sir, it will accelerate.
See, I'll tell you one thing. I'm having a balance on this 10 kg, on this 10 kg, right? Now it is perfectly balanced, correct?
Yes.
Understood?
Yes, sir.
Now very
Yes.
unfortunately, if this side, if it is increase, then which one is dominating? This side is dominating, correct?
Yes, sir.
Yes. So which side is more here? The motor side is more. When the motor side is more, the motor will accelerate or deaccelerate now?
The motor side is more, so it will deaccelerate.
The motor torque is more, it is accelerate, na? So you tell, see, you just imagine you are carrying some 10 kg weight, right? Understood?
Yes, sir.
When you are
Yes, sir.
carrying some 10 kg weight, you are spending some energy to carry that weight. You are
Yes,
walking
sir.
with some speed, right? Suddenly you had
Yes, sir.
some, you have suddenly some extra energy. Then you walk faster, you walk with the same speed.
Fast, sir.
So the same thing. So when the speed of the motor is reduced, the motor torque is increasing. That means the energy gained by the motor is increased. Then it will accelerate or it will deaccelerate.
Accelerate, sir.
So from 940 it will start accelerating, right? When it start accelerating, what
Yes,
happened to this motor torque now?
sir. It will
Decreases.
get to point A and it will be stable.
Yeah, it will be stable. Is it clear?
Yes, sir. Okay.
Clear, Gaurav?
Yes.
Right. Now your doubt got clear?
Yes, sir. Thank
Right.
you.
Right. Bharat. Bharat. Bharat.
Sir,
Huh.
sir, in torque slip characteristics,
Okay.
sir, third question, why after reaching Tmax torque is decreasing?
Why? Because after reaching the maximum torque, the speed will be very closer to ns.
Yes,
When the speed is very closer to ns, the relative speed will be very close. The relative speed is very less, correct?
yes,
Then flux cuttings will be
less,
when flux cuttings is less, EMF will be,
less,
then currents will be.
high,
Arey Baba, when EMF is less, how currents will be high? When EMF is
less.
less, so the current will fall drastically. So after that, why? Because the speed will be approaching very closer to ns, then that fall in current will evaporate. Why? Because flux currents will decrease as randomly. I mean, it falls like a ramp. Then the EMF will fall, the current will fall. So when current is falling like a ramp, even though the power factor is increasing, the torque will be decreasing. So which fall is like abrupt means the fall in current will be abrupt compared to the increase in power factor. So that is the reason the torque will be reduced. Understood now?
Yes, sir.
Which fellow will be falling like a ramp, the current will be falling like in faster rate it is falling. That is the reason the torque will also falls in a faster rate. Understood?
Yes, sir.
Sorry. Sorry. Just 1 second. Let me switch off this. Right. Yes, Bhavani.
గుడ్ ఈవినింగ్ సార్.
Good evening, ma. Please ask.
సార్ స్టడీ స్టేట్ ఆపరేషన్లో మీరు అన్నారు కదా వెన్ ఫ్యాన్ లోడ్తో కంపేర్ చేసినప్పుడు టీఎం అనేది ఇంక్రీజ్ అయ్యి టీమాక్స్ తర్వాత డిక్రీజ్ అవుతుంది ఎట్ పాయింట్ దే విల్ బి ఈక్వల్ అని.
It is not like increase or decrease, ma. It is a question. Starting which torque is dominating, the motor torque is dominating. Yes. So this domination will continues till both the torques are becoming same. Once both the torques are becoming same, then the steady state point is reached and the motor will run stably with that point. So during this process, the motor torque may be reaching the maximum value, again it may be coming down. So it is not bothered there. Understood?
సార్ ఈ టాక్స్ ని మనం ఫిజికల్ గా అబ్జర్వ్ చేయగలమా సార్? లైక్ సౌండ్ ఆర్ హియరింగ్ ఎనీథింగ్ సెన్స్ చేయగలమా మనం?
Okay, Nana. See, torque is nothing but a twisting effect. So can you see? So if you just hold the shaft, then you can feel the torque value. But we cannot like see. Visually you cannot see, you can feel. Why? Because if you just, you take that fan, right?
ఓకే.
And to use the excitation, you try to hold with your hands. And you try to switch on. You can see that there is a twisting force acting on your fan. That
Yes,
means you can feel the torque value. But you cannot see the torques. Understood?
అండర్స్టాండ్ సార్. అండ్ వన్ మోర్ సార్, మీడియం స్లిప్ ఆపరేషన్ అంటే ఒకసారి చెప్పారా సార్ నాకు కొంచెం?
Medium slip ante it is between full load torque and maximum torque.
ఓకే.
It is between full load torque and this we call it as overload region. This we call it as overload region.
ఓకే.
Right?
ఓకే సార్.
Still? Arthandam?
అర్థమైంది.
Right.
థ్యాంక్ యూ సార్.
Right. Right. अब्दुल रहमान.
मेरे को एक छोटा सा इंफॉर्मेशन चाहिए सर. हेलो, आवाज आ रही सर? हेलो
अब्दुल रहमान.
सर, आवाज आ रही सर? हेलो.
हाँ, या प्लीज.
हाँ सर, मैं
हाँ आई कैन. या प्लीज आस्क.
नहीं सर, कल आप बोले था सिर्फ इंडक्शन मशीन्स नहीं है सर, नहीं तो कौन सी भी नहीं है सर क्लास? हेलो.
So tomorrow you are not having any class, right?
अच्छा.
For all batches holiday.
अच्छा, मेरे जो पोर्टल में एफ&एस दिखा रहा था, इसलिए मैं पूछ रहा था मैं आप.
नहीं, I don't think. एक बार चेक करो. You are called to your schedule manager.
अच्छा.
Okay.
Okay, sir. Okay, sir. Okay, thank
Right,
you.
right. Ramakrishna. Oh, Ramakrishna.
Yeah, hello, good evening, sir. You have said
Good
that
evening,
you would
Baba.
give some reference name, books of name, so you didn't give
See,
what to practice, which books to practice, sir.
see, Baba. Yeah, already I told you that the books which you need to follow for this is Electrical Machines by Nagaratan Kotari,
Okay, sir. Kotari. Okay, sir.
Electrical Machineries by P.S. Bhimra.
Okay.
Okay.
Yes, sir. Okay.
Electrical Machines by Bhattacharya.
Okay, sir.
Right.
Hmm.
So these are enough.
Okay, okay, sir.
Okay. Right. Go.
Okay, thank you.
Right. Vijaya Rani Reddy.
Hello, sir.
Ha,
Hello,
Baba,
sir.
please. Ha, please. Ready.
Sir, I have a question, sir. Like, so when we are starting
You
induction
can ask
motor,
any.
sir, if we start induction motor, sir, with your load,
Yeah. I can hear you. Ready. Please ready.
then first the mechanical torque reaches to load torque, sir.
Electromagnetic torque becomes load torque.
Load torque, yes, sir. After that, if you increase the load, then the maximum mechanical torque occurs. After that, the machine.
The speed will.
After that, machine can't be rotated that load, sir. That is normal procedure, sir.
Yeah.
Sir, in torque slip characteristics.
Yeah, please tell.
Sir, in torque slip characteristics, in that graph, first T max came, and after that, full load torque will came, sir.
Correct. So this is with respect to which load I have explained. Full load. This is fan load. Correct.
Yes.
Correct.
Yes, sir.
Right. Let me
Normally,
assume that
after full load, we have to after full load T max will come, sir. But in the graph, first T max is there. After that, full FL is there, sir.
that is with respect to which load I told. Which load I told? Fan load.
So not fan load also, sir. Just
which load it is? Fan load.
No, sir. You didn't
See,
say any
Baba,
load, sir. At that time, you didn't say any load, sir. You just drawn the graph for torque slip characteristics.
So this is for which load? This is for which load?
This, sir. This one, sir.
This is which load?
Fan load.
Now this is clear with
Yes,
fan
sir.
load, correct?
Yes, sir.
Clear? Now let me answer
yes.
your question. Let me answer your question. Okay. Say the initial load on the motor is this one, constant torque load. So it is at 10 Newton meters. Let me assume.
Okay.
Okay.
Yes, sir.
Now this is your starting torque.
Yes, sir.
Then the motor will accelerate up to this point.
Yes, sir.
Now you are increasing the load.
Yes, sir.
The motor will decelerate and this torque will come.
Okay.
Now you are increasing the load. Then this is your full load. Then you are increasing the load. It can supply. When you are increasing the load beyond this, up to here it will supply. If you are increasing the load, then motor will come to standstill. This is with respect to constant torque load. But I have explained with respect to which load? Fan load. I hope you are clear with this. Ready?
Okay. So understanding the graph somewhat different, sir. Here.
Yeah. But I took which load there, Baba? Fan load. This is your constant torque load. I hope you are clear. Ready?
Okay, sir.
Understood?
Yes, sir. Yes, sir.
Right.
Sir, and also another doubt, sir.
Yeah, you can ask. Any doubt you can ask. Absolutely no issue.
Sir, so we are in rotor.
Hmm.
So we will find by using multimeter resistance, sir, rotor resistance per phase.
See, in case of slip ring, it is possible, but not in case of squirrel cage.
Okay, sir. Okay, sir. In case of slip ring only, it is possible to measure, sir. But so that leakage reactance, how you will find, sir?
See, leakage reactance cannot be measured. It can be only calculated. Right? How means? Generally, you know the definition for impedance.
Sir.
What is the
That is
definition for impedance? It is V by I.
Okay, sir. Sir.
And this is equal to square root of R square plus the leakage reactance square. You are measuring this using your so-called as VI method or Kelvin's double bridge, whatever it may be. And you are having this Z. The unknown leakage reactance can be calculated. Understood?
Okay. At starting, because of this VI parameters, we are saying inductance as a leakage reactance is more, like that, sir. Yes, sir. At starting, because
Yes.
of this V and I relations, we are saying that the leakage reactance is more at standstill.
It is not like that. At starting, the currents will be very high.
Yes, sir.
The currents will be very high. What about the magnetism produced by that current?
Currents will be very high.
Yes, I told
More,
you.
sir. More, sir.
The leakages will be?
Leakages will be more, sir. Sir, that leakages means what, sir?
See, they are the part of your
It is,
total flux lines.
that means the power which is most of the power it is used as magnetism, like
Reactive.
that, sir.
Correct.
Instead of rotating.
See, I have a disturbance at your back.
Okay.
Right. Now you please ask.
Okay, sir. I understand, sir.
Right. Okay.
Okay, sir. Thank you, sir.
Right. Right. Ravi Kumar. Ravi Kumar, Gandham.
Sir, good evening.
Good evening, Baba.
Sir, stability analysis.
Yeah. Yeah.
Sir, can you explain point B once again?
See, point B. What is the speed here? 500.
Yes, sir.
Let me consider due to the disturbances, the speed is reduced. To
Okay,
which
sir.
value? 490.
490.
When the speed is reduced, what happened to this motor torque from here? It has fallen. It is reduced.
Decreases.
But the
Yes,
load
sir.
on the motor is more or less. It is same. But the motor torque is reduced. So which torque is dominating now? Load. Then because of this load, the speed will still decrease. It will come here.
Oh. Okay, sir.
Like this, it will come like this, like this, like this, like this, like this. These points will come and automatic. Finally, the speed will come to standstill. Why? Because NR is equal to 0 like this. Understood?
Yes, sir.
Clear?
Sir, yes, sir. Clear, sir. Another one. Sir,
Yeah.
in unstable and medium slip is there. The diagram.
Yeah.
Sir, once explain the stable and unstable regions. One.
See, you just refer my previous notes. If torque,
Actually, yes, sir, I missed a class before session.
right. See, if torque is directly proportional to S, stable region or unstable region?
Actually, I missed a class before class.
Yeah, refer that notes, right? After that, you call to me. Okay?
Yes. Okay, sir. Thank you.
Right, Baba, right. 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 So I'll stop for today because no one is raising the hands. We'll meet on Monday. Thank you. Good luck for your exams.